By 1930, the search for the elusive ninth planet had been running for well over 3 decades. Since the turn of the 20th century, precise observations of the orbits of Uranus and Neptune had suggested that there was something else lurking in the darkness of the outer solar system, another distant world far beyond Neptune. But hunting down such a faint object was like looking for a needle in the celestial haystack. Leading the search for Planet X over much of this time was the founder of the Flagstaff Observatory, Percival Lowell. Starting in 1906, Lowell had embarked on an obsessive pursuit of the ninth planet, but despite years of work, he would not live long enough to see its discovery, and he would never know how close he came to finding it himself. Unknown to Lowell, an image of Planet X had been captured in 2 photographs he had taken just a year or so before his death in 1916. But the evidence was missed. The photographic plates were filed away, and the search would go on without him for another 15 years. The logic behind using identical pairs of photographs taken a few nights apart was simple. By examining the 2 images for any stars that appeared to have shifted position, they would be able to differentiate between the distant stars in the background and anything that was orbiting closer to Earth. Hundreds of pairs of images were taken at the Lowell Observatory for this purpose, and analysed using a blink comparator, which helped to reveal any minute differences between the images. But it wasn't until the night of the 29th of January 1930 that Tombaugh would strike gold. Comparing the 2 images he had taken a week apart, Tombaugh discovered what appeared to be a moving object on the 2 plates. Across those few days, a dim spot had moved no more than an inch, but that movement signified something profound. This was an object much closer to the Earth than the distant stars in the background, an object that had moved as our perspective had changed with the Earth's own orbit. And over the course of that week, this object appeared to have shifted against the distant background. Tombaugh had found Planet X, which would be named Pluto, after the suggestion of Venetia Burney, an 11-year-old English schoolgirl from Oxford with an interest in classical mythology. Taking off from Cape Canaveral Air Force Base on the back of an Atlas V rocket, the New Horizons space probe began its epic journey across the solar system towards Pluto in January 2006. Just 9 years after the death of Clyde Tombaugh, this tiny interplanetary probe, no bigger than a grand piano, made room in its payload for 30 grams of his ashes, a tribute to the man who had begun our journey to Pluto 76 years before. For Alan Stern, principal investigator of the New Horizons mission, this move fulfilled a promise made to Tombaugh. Shortly before New Horizons became a project, while we were still trying to get funding to fly a spacecraft to explore Pluto, Clyde died in January of 1997, and prior to that he had asked if a mission ever did get launched, if there was a way it could be considered if some of his ashes could be sent on the journey. And I had heard about that back in the 90s, and when it came close to launching New Horizons in the summer of 2005, I reached out to his family to see if that's something they wanted and it was still possible. And it was, and we found a way to do it, and we were very proud to be able to make it happen. Not just for Clyde Tombaugh and his family, but even more so for the people of Earth, because it makes a very human connection between the discoverer of this world and those who were the explorers of it on the New Horizons team. Leaving the Earth with an escape velocity of 16.26 kilometers per second, New Horizons was the fastest probe ever launched from our planet. Reaching Jupiter in just over a year, it progressed on its way with a gravity-assisted kick from the gas giant, sending it hurtling across space. With all non-essential systems shut down to conserve energy, this little probe would sleep through most of its epic 8-year voyage in the dark. After 20 years of planning, building, and dreaming, the New Horizons team could only wait and hope for its safe passage as it made its way towards the last unexplored world in our solar system. But while the voyage itself proceeded without a glitch, back on Earth, the status of the mission was about to take the most unexpected of turns. Starting with the discovery of the rocky object 15760 Albion back in 1992, The description of Pluto as a planet, orbiting alone in the farthest reaches of the solar system, would come under increasing scrutiny. Pluto, it seemed, was not so lonely after all. This was a region of space filled with an array of orbiting objects, and as we began to peer into the Kuiper belt, we discovered they were far from just fragments. This was a region of space filled with Pluto-like worlds. 50000 Quaoar, an object half the size of Pluto, discovered at the Palomar Observatory in June 2002. 90377 Sedna, a large minor planet discovered in November 2003 on an 11,400-year orbit around the Sun. 136198 Haumea, a huge pebble-shaped world with two tiny moons in orbit, discovered in December 2004. 136472 Makemake, a dwarf planet perhaps two-thirds as big as Pluto, discovered in 2005. Then, in January 2005, we spotted 136199 Eris, a world almost the same size as Pluto itself, if not bigger. These discoveries, and the hundreds we've made since, forced the International Astronomical Union, the ruling body on Earth for all things astronomical, to formally reconsider the definition of a planet. In October 2006, they published a set of 3 criteria that any object in our solar system would have to fulfill if it wanted to stake a claim of planethood. 1. It has to orbit the Sun. 2. It has to be massive enough for it to form a sphere under its own gravity. 3. It has to be massive enough to clear its own orbit of any other objects, dust, or debris. Pluto certainly ticks the first box, completing an orbit of the Sun every 248 years. We also know, even from our most distant observations, that Pluto is nearly perfectly spherical, and so the second criterion is also a clear tick for Pluto. But when it comes to the third requirement, Pluto is not so lucky. It is simply not massive enough to blow away all the bits of dust and debris in its orbit, and for that reason, it fails to make the cut as a planet. Since September 2006, Pluto has been officially designated a dwarf or minor planet. A sphere orbiting the Sun, yes, but a planet, no. The third criterion is ultimately the one that necessarily separates the chosen 8, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, from the rest of the globes that orbit the Sun. Because if Pluto was a planet, so too would be Sedna, Eris, Makemake, and all the other tens or potentially even hundreds of smaller objects that orbit in the distant Kuiper belt, billions of kilometers from the Sun. So for now at least, we have a solar system filled with 8 planets, but many worlds. Hundreds of moons and dwarf planets, many that remain unknown and out there waiting to be discovered. As for Pluto, despite the best efforts of complaint and protest around the world, by the time New Horizons entered the final leg of its epic voyage, it had changed from a mission of planetary exploration to the first ever mission to a dwarf planet in the Kuiper belt. Thankfully, our solar system pays little heed to the fanciful definitions of humans from the International Astronomical Union, and while downgraded by name, the world that awaited us was anything but a disappointment. After nearly 10 years alone in the icy darkness of space, New Horizons awoke from its state of hibernation, and the pixels that Hubble had seen all those years before were at last replaced by our first glimpse of the most distant world we have ever visited. In July 2015, New Horizons began to beam back images from its close encounter, to reveal Pluto not as a frigid, featureless, frozen rock, but something far more beguiling. Planet or not, Pluto was beautiful. The images revealed a complexity of character stretching across its freezing -230 degrees Celsius surface that contained all the features of a dynamic, active world. The blemishes we'd gazed at from a distance were no longer just smudges, but high-definition images revealing an extraordinary range of geological form and structure. New Horizons first spotted Pluto shortly after launch, just a dot in the distance. And year by year that dot grew a little brighter. But even after 9 years of flight, it was only 2 pixels across. And we were only 10 weeks from arrival when the blurry images were as good as the Hubble had been able to do all that time. But then they got a little better, and a little better, and a little better. And suddenly, overnight, as we flew past, it went from a kind of naked-eye vision of what the moon looks like, where you can see the general patterns of bright and darkness, to all of a sudden this phenomenally complex world, with mountain ranges and gorges and glaciers, and an atmosphere glowing up to 500,000 feet in the sky, and polar caps, evidence for a liquid ocean on the inside, 5 spectacular moons, and so much more. It was almost overwhelming in the first days and weeks after to see what an amazing place Pluto was, and I took to saying that the solar system had saved the best for last. Alan Stern, New Horizons mission. This was a landscape built from frozen nitrogen, with soaring mountains and complex ridged terrain with a look of snakeskin. But one feature more than any other leapt from the images New Horizons fed back to us. Running across the equatorial region of the planet, we could see a giant heart-shaped plain of frozen nitrogen, methane and carbon monoxide that stretched for 1 million square kilometers, a region that has been named Tombaugh Regio, or to give it its more popular name, Pluto's heart. The western lobe of the heart is called Sputnik Planitia, and at its eastern edge lies a range of mountains made of pure frozen water ice that rises miles above the frozen plain. But it wasn't just the soaring mountains and romantic form of this region that caught the eye. There was something else about Sputnik Planitia, a strange detail that set it apart from the rest of the dwarf planet. Everywhere we looked across the surface of Pluto, we saw a world covered in craters, the scars of impacts that, just like on the surface of our moon, have taken place over billions of years. Except on Sputnik Planitia, this icy plain appeared unblemished, an utterly smooth surface, untouched for mile upon mile without a single crater to be seen. And the closer we looked at this region, the stranger it appeared, because as we studied the detailed imagery beamed back by New Horizons, we saw a puzzling set of patterns and shapes across its surface, a series of hexagons and pentagons crisscrossing the frozen nitrogen exterior that suggested something intriguing was going on beneath. New Horizons had provided us with a hint that Pluto's heart was beating. The geometric patterns we see on the surface of Sputnik Planitia may be distant, but they are remarkably familiar. We see these patterns all across nature, from the surface of the sun to a pot of boiling water. They are the characteristic patterns of convection, the forms we see when a heat source causes material to rise up and then fall back down again as it cools. So it seems that underneath the surface of this region of Pluto, there is a heat source which is creating a circulating convection current, melting the nitrogen ice and causing it to rise, cool, and then fall again, constantly resurfacing the area, removing any scars from impacts, and leaving the characteristic cells of convection behind. We don't know for certain where the heat is coming from that has shaped this distant world, but many scientists now believe that below the surface of the glacier there was once a liquid body of water, a flowing ocean that might even still be there. It's this ocean that could possibly explain the strange patterns on the surface, because it needs only a small difference in temperature between the underground ocean and the frozen nitrogen above to create the convection currents needed to produce the crater-free patterned plane we see today. Just imagine that billions of miles away from the sun, on the frozen frontier of the outer solar system, there may still be an ocean of water. And what is above this lonely, distant ocean? As New Horizons left Pluto behind to continue its lonely voyage out into the darkness, NASA turned its camera back towards the dwarf planet, revealing a hazy atmosphere made mostly of nitrogen, a blue sky above an ocean of water, 4.8 billion kilometers from Earth. Today, New Horizons, just like Voyager 2, continues onwards, heading out into the furthest reaches of our solar system. In January 2019, 3.5 years after leaving the beating heart of Pluto behind, it revealed a new world, the first image of 2014 MU69, otherwise known as Ultima Thule, the snowman dwarf planet. By visiting these outer worlds, we have momentarily illuminated the darkness, found and explored worlds far beyond our imagination, and opened a new and as yet unfinished chapter in the story of our solar system. It's a story that began with the formation of an ordinary star a little less than 5 billion years ago, a star that would leave just the right ingredients for 8 planets and countless worlds to form in her shadow. Jupiter came first, the godfather that would cast its hand across all that was to follow, shaping the destiny of the solar system as it wandered near and far. In Mars, it would leave a world too small to fulfill its potential, chasing the destiny of its nearest sibling before rapidly slowing down. Venus would soon follow, an oasis in its earliest of days, choked by the intensifying grip of its atmosphere. Just like Mercury, it would find itself too close to the sun to hold on to its charms. Only one planet, our own, has held on to its oceans beneath the thinnest of veils. A world that, through the luck of its formation, has not only sparked life, but nurtured it as well. For 4 billion years, our planet has remained stable long enough to allow the most curious of minds to evolve, look up, and explore. This is our story. A story that we now know not only has a beginning and a middle, but an end too. An end that will see the islands of life in our solar system shift from one world to another, until perhaps in the final days of our star, it will be Saturn that harbors a world where a life form can call it a home. We've written this story not with imagination, but with exploration. A story just like the very greatest of our legends that will be added to and heightened as it is passed down the generations to come. Where it will end up, I do not know. Lost with our planet, or carried onwards to distant worlds, its destiny and our destiny are unmistakably entwined. Why do we explore, some people ask? Shouldn't we focus on solving our problems here on Earth before spending time and energy and resources reaching for the stars? Well, I think that focusing entirely on our mote of dust would be a profound mistake. It would mean that we've taken the decision to sit huddled in a tiny corner of the solar system, wondering what we're doing here. It would mean that we've taken the decision to fight among ourselves for ever more precious resources, confined below a thin shell of air to the 2-dimensional surface of a small rock, rather than following the 3-dimensional path marked out by the lights in the night. We need to shift our focus. We live in a solar system of wonders, of planets of storms and moons of ice, of landscapes and vistas that stir the imagination and enrich the soul. A system of limitless resources, limitless beauty, and limitless potential. If we don't go there, we'll never go anywhere. And if we go nowhere, then we'll have no future at all. To the Romans, Jupiter was the king of the gods, the ruler of the heavens, and a figure of power who drove forward the all-conquering Roman army with a thunderbolt in one hand and an eagle by his side. The name Jupiter itself means sky father, and it's constructed from the Latin words dies, day or sky, and pater, father. And, as is often the case with mythology, there is a truth lurking amongst the legend. In size alone, Jupiter is by far the biggest planet in the solar system. Its mass is a staggering 1,900 trillion kilograms. That's 2.5 times bigger than all of the other planets in our solar system combined. It's so big, in fact, that if you were an alien species observing our system from a distant part of the galaxy, the Sun and Jupiter might well be all you could see. With a diameter of 142,984 kilometers at the Jovian equator, the Earth would fit inside Jupiter over 1,300 times. And yet this giant of a planet is made almost entirely of gas, comprising 89% hydrogen and 10% helium. It is far less condensed than any of the rocky planets, and has a density far smaller than that of the Earth, 1.326 grams per cubic centimeter, compared with Earth's 5.513 grams per cubic centimeter. For all of its size, Jupiter also has the shortest day of any planet, completing a single rotation every 9 hours, 55 minutes and 30 seconds, as it whips around on its axis at 45,000 kilometers an hour. In the last 50 years, our knowledge of Jupiter has grown exponentially, and with it we've gained a deeper understanding of the role it has played in the shaping of the solar system. No longer just the beautiful banded world we see through our telescopes. This is a planet that we have explored up close, our eyes and ears living within the Jovian system for years at a time. The first close-up glimpse of the giant planet came with the cameras of the Pioneer 10 spacecraft in 1973. This was the first of our planetary explorers to cross the great boundary of the asteroid belt, and from an approach of just over 130,000 kilometers, it was able to take close-up images. In total, Pioneer 10 sent back over 500 precious pictures of this distant world, before flying onto the very edges of the solar system to complete its mission. Just over a year later, Pioneer 11 followed hot on the heels of its sibling craft and swept within 43,000 kilometers of Jupiter's cloud tops before heading on towards Saturn. Voyager 1 and 2 passed by Jupiter in the late 1970s, taking the first extraordinary images of not just the planet but its moons too, as part of their own grand tour of the solar system. This was an historic moment, as Fran Bagenal, scientist on the New Horizons mission, explains. We had hints, but it wasn't until Voyager went up close and personal and took amazing pictures of the moons of the planet that we really began to get a sense of just how complex the worlds around Jupiter are, and what a variety there is. The Galileo spacecraft became our first explorer to actually live in the Jovian system. Entering orbit around the planet on the 7th of December 1995, Galileo spent 2 years touring Jupiter and allowed us to explore as never before. Thanks to its audacious deep dive directly into the planet, a probe that was released from the craft collected data for almost an hour as it parachuted down through 150 kilometers of Jupiter's atmosphere, before it was destroyed by the intense pressure and temperature. Galileo was also the first mission to explore the extraordinary moons of Jupiter in any detail, helping us to see for the first time that Jupiter lies at the center of an extraordinary system with more natural satellites than any other planet, holding 79 moons in its orbit at the time of writing. 12 of these satellites have been discovered since the beginning of 2017. It's almost certain that the number will rise in the coming years too, as we're able to explore the Jovian system in even greater detail. The vast majority of Jupiter's moons, 63, are not much more than fragments of rock, none bigger than 10 kilometers in diameter, and are captured asteroids that now orbit the planet rather than the Sun. But at the other end of the scale, Jupiter has 4 giant moons. Fiery Io is the most volcanically active world in the solar system, its surface littered with lakes of lava, while icy Europa is at the other extreme, with its frozen surface protecting a global ocean of water beneath. Marbled Ganymede is Jupiter's largest satellite, and the only moon we know of that has its own magnetic field, while Callisto, the outermost of Jupiter's Galilean moons, is also thought to be home to a subsurface ocean. Each moon has a unique, intriguing character, and they are all visible to us here on Earth, using nothing more than a pair of binoculars. Then, in August 2011, NASA launched its latest mission to Jupiter, Juno. After traveling for 5 years, the spacecraft reached Jupiter in July 2016, and entered into a perilous elliptical orbit that took it from 8 million to just 4,000 kilometers above the cloud tops of Jupiter's surface. Juno is a mission designed to probe for Jupiter's origin and evolution, which it does by carrying instruments to measure the planet's composition and its magnetic and gravitational fields, allowing it to build up a detailed picture of the interior. It also has the best camera we've ever pointed at Jupiter, which since 2016 has been sending back the most incredible images of the giant planet ever taken. We'll let Heidi Becker, a Jet Propulsion Laboratory physicist and the radiation monitoring investigation lead on the Juno mission, explain the detail of this incredible piece of technology. The Star Tracker is an 18-pound camera because it's passed with tungsten in order to keep the radiation out. What JunoCam's images have shown us is that Jupiter is like going to an impressionist art gallery. It's seeing Jupiter and those atmospheric features up close with the highest resolution that's ever been achieved. We're seeing the zones and belts, the jet streams of Jupiter, in more detail than ever before. For all the majesty and wonder these probes have brought us, Jupiter remains a vast, distant planet, sitting on average 588 million kilometers away from us here on Earth. It's easy to think of this world as a benign beauty, a jewel to marvel at. But what makes Jupiter the true king of the heavens is not just its beauty, but its influence over the unfolding story of the solar system. As we've explored this world ever closer, we're discovering that Jupiter's effect on the fates of entire planets is far more direct and violent than we ever imagined. Its massive gravitational field exerts control not just over its moons, but also over every asteroid, every world, and every life force in the solar system, whose destinies it still holds in its vast reach. To understand the awesome power of Jupiter, we don't need a billion-dollar spacecraft, a rocket, or even a telescope. All we need to do is to look no further than the ground beneath our feet. The surface of our planet is littered with the evidence of our distant godfathers' meddling. Written across our planet in the violent gravitational handiwork of Jupiter are, at the most recent count, 190 visible impact craters, not to mention the thousands more that have long disappeared as the active geology of the Earth's surface has continually renewed itself. One of the most famous is the Meteor Crater, also known as the Barringer Crater, in the northern Arizona desert, which measures more than 1,000 meters across and at its deepest point drops 100 meters below the crater rim. In the late 19th century, geologists believed this vast feature had been created by the San Francisco volcanic field that lies just a handful of miles to the west. But in 1903, Daniel Barringer, a mining entrepreneur and sometime hunting friend of Theodore Roosevelt, began an extensive investigation of the crater and published a set of findings suggesting that it had not been created by a volcano, but rather by a large incoming projectile from outer space. This was the first time anyone had suggested such a theory, and Barringer backed it up with a host of geological evidence, including the discovery of around 30 tons of large iron oxide fragments from the suspect meteorite. At the time, there was much skepticism that an incoming meteor could create such a massive geological feature. But ignoring the overwhelming scientific consensus, Barringer put his money and reputation firmly where his mouth was and formed the Standard Iron Company. The company was created with the sole aim of mining the crater for the 100 million tons of iron ore that Barringer believed lay in the ground, having been deposited by the incoming meteorite. Even at 1903 prices, if he'd been right, that amount of iron ore would have been worth over $1 billion. So unsurprisingly, he continued to dig down to depths of over 400 meters in his pursuit of the meteoric remains. Unfortunately for Barringer, it would take him 27 years of mining to find out what we know today. The meteorite that impacted in that Arizona desert was not only much smaller than he predicted, with current measurements suggesting it was around 300,000 tons, 300 times less than he had thought, but also, with the benefit of advanced studies in such impacts since then, most of the nickel-iron meteorite that fell was vaporized as it struck the ground at around 43,000 kilometers per hour. Barringer's money evaporated not quite as quickly as the meteorite, but by 1929 operations at the site had stopped, and most of his fortune had gone. It would be 50 years before Barringer's work would be fully and finally verified with a landmark publication in 1963. Analysed the similarities between the geology of the Barringer site and the craters that had recently been created as a result of testing nuclear weapons in Nevada. Shoemaker was able to show that the shocked quartz, also known as coesite, that was identified at Barringer crater, could only have been formed at the enormously high pressures and temperatures created by a nuclear explosion, or in the case of the Arizona crater, by the extraordinary impact dynamics of a 300,000-ton meteorite crashing into the ground. We know now that the giant rock that created the crater, like most of the meteorites that strike the Earth, was once an asteroid, just one of the millions of rocks that circle the Sun between the orbits of Mars and Jupiter. Most of these have been in a stable orbit for billions of years. The rocky leftovers of the birth of the solar system, they orbit in an eternal junkyard of planetary cast-offs. But occasionally, one of these huge rocks is propelled towards the inner solar system, and more often than not, we think the nudge that causes it comes from Jupiter. Why this should happen, and how Jupiter exerts its power not just over the asteroid belt, but over all the worlds around our Sun, is a story we are only just beginning to understand. From our home here on Earth, it's hard to imagine the vast reaches of space that extend beyond our little bubble and the huge expanse of time over which events in the cosmos play out. But all the evidence suggests that around 4.5 billion years ago, Jupiter's orbit began to change, and as it did so, it triggered a period of unprecedented violence, during which the young solar system was utterly transformed. We know this because the marauding planet left a trail of destruction in its wake that we've only just begun to explore. As we've attempted to uncover the 5 billion-year history of our solar system, we've repeatedly looked to the 8 planets and the moons that orbit them to provide clues that fill in the gaps in our story. In the last 50 years, dozens of missions have crossed our thin blue line on the way to those worlds, but only once have we sent a spacecraft to explore a very different type of world, to search amongst the rubble of our solar system's earliest days and explore the handful of worlds that never quite made it. Sometimes the answers lie in the gaps. Launched on the 27th of September 2007, the Dawn space probe took off from Cape Canaveral on a mission to explore the 2 largest objects in the asteroid belt, Vesta and the dwarf planet Ceres. This $450 million project was part of NASA's low-cost Discovery program, one of a series of missions designed to be faster and cheaper to deliver. But this was no B-list mission for NASA. Equipped with the most advanced ion propulsion system ever used in outer space, Dawn would be able to reach the asteroid belt and become the first craft in the history of human exploration to enter orbit around Ceres. And yet, without a major planet in its itinerary, the attention of the world only seemed to glance towards this mission, and for the most part its extraordinary findings slipped between the gaps of public attention. The aim of the Dawn mission was simple. This would be the first spacecraft to travel to the asteroid belt, the first to orbit an object in this uncharted region of the solar system, and the first to visit a dwarf planet. All in all, this mission profile was designed to allow scientists a rare chance to travel deep into the past and glimpse the earliest moments in the origin of our solar system. The mission allowed us to explore the evolution of Vesta and Ceres, 2 very different objects, frozen in time for billions of years since they faltered and failed in the process of becoming fully fledged planets. To travel to the asteroid belt would be a slow but steady voyage for Dawn. After hitching a conventional ride into space on the Delta II rocket, the spaceship began firing its thrusters to orientate and propel itself away from the Earth and towards Mars. The ion thrusters on Dawn were an efficient but gentle form of propulsion for the spacecraft, taking 4 days at full throttle to accelerate the craft from 96 kilometers per hour. It's not exactly a sports car, But when it comes to efficiency, the ion propulsion system is difficult to beat. Powered by a 10-kilowatt solar array, Dawn's engines ran for almost 6 years across the 11-year lifetime of the mission, propelling the craft across space using less than 400 kilograms of its xenon fuel supply, while reaching speeds of 41,360 kilometers per hour. Its trajectory took it on a 16-month journey to Mars, where a gravitational kick sent it on its way out to the asteroid belt and onwards towards Vesta, its first destination. Almost 500 million kilometers from the Sun, the asteroid belt lies halfway between Mars and Jupiter, the boundary line between the 4 rocky worlds that orbit closest to the Sun and the giant gas and ice planets that lie beyond. Made up of millions of pieces of rock from the dawn of the solar system, it's a graveyard of failed planets, remnants from the heyday of planetary construction. We often imagine the asteroid belt to be a dense, unnavigable mass of tumbling rock, but in reality it's something quite different. The total mass of all those rocks is estimated to be 3 times 10 to the power of 21 kilograms, which, although an enormous-sounding number, is just 4% of the mass of our Moon, with a third of that mass found just in the largest object series. The rest of this cosmic junkyard is made up of objects covering a vast range of different sizes. On one end of the scale, we think there are at least a couple of hundred asteroids larger than 100 kilometers in size. Then come a million or so stretching to at least 1 kilometer or more, and a countless spread of smaller objects number in the millions and billions, depending on how small you want to go. All of this sounds like it should make for a crowded environment full of collisions, the perfect location to form the basis of a computer game or disaster movie. But even with that many objects, the space they occupy is so unimaginably vast, spread out across 13 trillion cubic miles of space, making the average distance between any 2 large asteroids approximately 2 million miles, or 8 times the distance from the Earth to the Moon. These distances are so large that when we send spacecraft to the outer solar system, the chances of hitting anything are so small that the engineers don't need to make any course corrections to pass through. In fact, if you were standing on an asteroid, you'd be lucky to see another one, and if you did, it would appear as little more than a tiny point of light in the darkness. As it travelled through this vast emptiness in the early summer of 2011, the Dawn spacecraft slowly began to bring its first target into view. From a distance of over 1.2 million kilometers, Dawn took its first photograph of Vesta against the backdrop of 1,000 stars. Over the next 2 months, Dawn homed in on Vesta, chasing it across the vast reaches of space to arrive at this, the second largest rock in the belt. Entering its orbit on the 16th of July 2011, Dawn became the first spacecraft to enter within the gravitational hold of an object in the asteroid belt. And for the next 14 months, it would explore this extraordinary ancient object, providing a glimpse of our solar system in the very earliest days of its life. When 4 Vesta, to give it its full name, was first discovered by the German astronomer Heinrich Olbers in 1807, it was the 4th asteroid to be discovered after Ceres, Pallas, and Juno, hence the 4 in its formal designation. Olbers was convinced he had found the remains of a lost planet, destroyed in some long-ago collision. Even so, just like the other 3 objects, at first Vesta was given full planetary status, bringing the number of classified planets in the solar system at that time to 11. It wasn't until 1845, nearly 40 years later, that a flood of further discoveries began that quickly increased the number of objects in this region to a point where it was clear they couldn't be classified as planets. And so in the 1850s, 15 planets became 8, and the classification of these objects as a different class of minor planet, asteroids, had begun. 160 years later, as Dawn began its year-long residency in the vicinity of Vesta, it soon became apparent that Olbers' suggestion that this was a fragment of a long-lost planet was not so far off. Vesta is a spheroid-shaped rock, 530 kilometers in diameter and pockmarked with impact craters. The most striking example of these is the crater Rhea Silvia, which at 500 kilometers wide and 20 kilometers deep is one of the largest impact craters in the solar system. At its center is a mountain that rises into the blackness 22 kilometers from the crater floor, making it the second tallest peak in the solar system after Mars's Olympus Mons. What's particularly extraordinary about this crater is that we've long suspected that a particular class of meteorite found on Earth, known as HED meteorites, actually come from material that was blown off the surface of Vesta when this impact occurred around 1 billion years or so ago. Using Dawn's instrumentation, we were able to directly measure the geology of rocks in Rhea Silvia, and when compared with the samples on Earth, we were able to conclude that they are of the same origin. In one of the most beautiful examples of geological analysis in the history of the subject, we now know that we can hold a piece of this faraway asteroid in our hands and directly analyze the secrets hidden within it. When taken all together, the HED meteorites and the findings from the Dawn spacecraft have enabled us to paint a detailed picture not just of Vesta today, but also of its history. Dawn has revealed to us that Vesta has a metal-rich core, just like all of the terrestrial planets, including Mercury, Mars, Venus, and Earth. And analysis of its surface geology has enabled us to date the formation of the asteroid to a couple of million years after the first solid objects began to take shape in the solar system. These are just two of the clues that point us to an extraordinary conclusion. Vesta is perhaps the last remaining example of a protoplanet, a half-formed world from the very earliest days of the solar system. Frozen in time, this is a stage that every world we know of passed through, including the Earth. Vesta was on the way to becoming a planet almost 4.5 billion years ago, but something happened to stop its progress. While other worlds went on to flourish, and other protoplanets disintegrated in the violent collisions of the early solar system, Vesta somehow seemed to survive, a fossil of planetary formation for us to not only look at, but through a quirk of fate, actually hold. But this was not the end of Dawn's dive into our deep history. Departing Vesta after 14 months of study, Dawn fired its ion drive, leaving the orbit and heading off for its second planetoid rendezvous, at the largest of all the asteroids, Ceres. Dawn arrived at the dwarf planet Ceres in early March 2015, and from the very first moments of its observations, it sent back some astonishing images. Very little was known about Ceres before our spaceship arrived, but it soon became clear that this was a rock with far more of a story to tell than we could ever have imagined. A story that would help reveal a new perspective on the deep history of our solar system and the enormous influence Jupiter has exerted over it. The Italian astronomer Giuseppe Piazzi discovered Ceres on the 1st of January 1801, and at first he reported his findings as the discovery of a new comet in the region of space between Mars and Jupiter. But it seems from the start that all of his instincts told him this was something else. In announcing his observations in a letter to two fellow astronomers, he noted that since its movement is so slow and rather uniform, it has occurred to me several times that it might be something better than a comet. Piazzi and his colleagues speculated that rather than a comet, they might have found something even more spectacular, a new planet. But after just 41 days of observation, Piazzi fell ill. The path of the newly discovered object strayed into the direct glare of the sun, and in a twist of high astronomical drama, the newly found planet Ceres was lost. With just a tiny number of observations across a small piece of sky, calculating Ceres's orbit was deemed impossible using the mathematics of the time, and many contemporary great mathematical minds predicted it might never be found again. It would take the work of a young German mathematician, Friedrich Gauss, to solve the problem. Attracted to the difficulty and elegance of using mathematics to compute the orbit from just a few coordinates, Gauss pioneered a novel mathematical method that allowed him to calculate the path of Ceres using just 3 of Piazzi's original observations. On the very last day of 1801, 2 astronomers using Gauss's methods searched the region of the sky to which the calculations guided them, and to everyone's delight and relief, recovered Ceres from the darkness. Gauss became a mathematical superstar, and Ceres, firmly back in our sights, was stamped with the classification of a planet. For the next 50 years, Ceres and its companions, Vesta, Pallas and Juno, remained listed as planets until, as we have seen, the discovery of a raft of other objects in this region of space gave rise to our identification of the asteroid belt, and for Ceres it was downhill from there on, until in 2006 it was classified as a dwarf planet. For the next 160 years, little was known about this tiny planet orbiting the Sun at a distance of 413 million kilometers. We knew that it was the biggest object in the asteroid belt, and the only object amongst the millions of asteroids that was large enough to have been rounded by its own gravity. We could also make a good approximation of its size, at around 1,000 kilometers in diameter, and composition, rock and ice, what else? But when it came to surface features, even the powerful eye of the Hubble Space Telescope could make out only the vaguest of features, intriguingly strewn across its surface. It would take Dawn's arrival for us to truly understand the complexity of this world and its history. Even in the early approach phase of the mission, Dawn was able to capture a quality of imagery that at once gave a new perspective on the long-hidden surface. It was no surprise to find it heavily cratered, but while speeding towards Ceres, Dawn beamed back a series of mysterious images, revealing a number of bright spots on the surface of what we had thought would be a dull, dead and frozen world, not what you would expect on a planet that was assumed to be entirely geologically inactive. The brightest of all of these highly reflective areas was imaged near a massive crater known as a crater. At 92 kilometers wide and 2 kilometers deep, it's one of the biggest on the surface of Ceres. Spot 5, as it became known, is in the center of the crater and became the focus of intense investigation as Dawn began its 3.5-year residency in orbit around Ceres. The crater is thought to have formed from a large-scale impact around 80 million years ago, and so the presence of what appeared to be geological active material on the surface was particularly surprising, and at first left the mission scientists perplexed. Not only that, but a haze was also seen to periodically appear above Spot 5, suggesting something was going on beneath the surface. After detailed analysis using Dawn's full range of imaging and spectroscopic capabilities, we now believe that Spot 5 is the result of a geological hotspot. The brightness created by the highest concentration of carbonate minerals ever found outside the Earth, in a dome structure right in the center of the crater. Why does this matter? Well, we know that this type of salt can only be formed in the presence of liquid water, and it's almost certain that an impacting asteroid could not have delivered such material to the surface of Ceres, so the upwelling in which it's found suggests that it comes from deep within this world. It now seems that Spot 5 is the remains of an ice volcano, one that is perhaps still partially active, and thus able to create the haze we have observed. The two brightly coloured patches inside it are thought to be the salty residue left by this ancient formation, deposits of sodium carbonate from an erupting ice volcano that may have first been triggered by the impact that created the crater. However, the dome-like shape upon which the deposits sit is almost certainly evidence of geological activity below the surface, suggesting that hydrothermal activity was involved in bringing the salts to the surface. And Spot 5 is far from isolated. We've now seen areas like the ones in Akator all over the surface of Ceres, and this begins to paint a tantalizing picture of Ceres' past, a past where heat from within the planet created a subsurface ocean, or at least localized pockets of water that surged upwards in the form of great ice volcanoes, bringing with them on the asteroid the carbonate salts that we see sparkling today. As Dawn delved deeper beneath the surface, the surprises kept coming thick and fast. Dawn was able to accurately measure the overall density of Ceres and found it to be 2.16 grams per cubic centimetre, which is less than you'd expect for a rocky body. Ceres is about 2/3 the density of our Moon, which suggests that as well as rock, the asteroid must also hold significant amounts of water ice. This had been suspected long before Dawn arrived, But with our eyes and ears now at work, as Dawn circled Ceres, it was able to take precise measurements and so uncover anomalies in its orbit that revealed something remarkable about this lump of rock and ice. By carefully mapping the shape and gravitational field, we found that the rock and ice weren't evenly distributed. It appears that Ceres' interior is nothing like that of other asteroids in the belt. Instead, it appears to have a rocky core surrounded by an ice-rich crust. This is not the jumbled structure of an asteroid. The differentiation into layers that was discovered by Dawn is something we only see in planets. It seems that around 4.5 billion years ago, Ceres had taken its first steps to becoming a fully fledged world, and then something went catastrophically wrong. So we now think that 4.57 billion years ago, a young rocky planet began to form in the region we call the asteroid belt. In its infancy, this protoplanet was a water world, warmed from within by the heat left over from the violence of its birth. Even in this frozen region of space, orbiting 413 million kilometers away from the weak young sun, a deep saltwater ocean encircled the young Ceres, protected from the freezing temperatures of space beneath a thin layer of ice. Across this ancient embryonic world, ice volcanoes broke through, transforming and renewing the surface as it was bombarded by the bodies that swarmed around it. Today we see just the lifeless remains of this geologically active world in the distinct mountainous landscape and sparkling salts that clothe it. But the subsurface ocean is long gone, locked away as a thick layer of ice between the surface and the core. This is a nascent planet that has been in deep stasis for billions of years. Frozen in time, it is a precious piece of history, an artifact that allows us to glimpse our origins and understand just how precarious a time this was for every planet, including our own. We now think that before Ceres could fulfill her potential, a great disturbance sent shock waves through what would eventually become the asteroid belt and cut its young life short. The vast amounts of rock and ice that made this part of the young solar system such a rich breeding ground for the birth of planets was wiped clean of almost all of its building material, leaving just a fraction of the material needed to build a planet, and nothing from which Ceres could grow. Computer simulations suggest that originally the asteroid belt contained enough material to build a planet the size of Earth, and perhaps that was once Ceres' destiny. Perhaps it was even destined to become a subterranean water world capable of supporting and nurturing life. But before any carbon chemistry could spark into seeds of life, Ceres' fate was sealed, triggered by the wanderings of a giant that lay beyond in the darkness. We now suspect that at this early time in the life of the solar system, as Jupiter circled the young sun, something caused the giant planet to change course and spiral inwards towards the sun, ploughing right through the asteroid belt. The resulting gravitational chaos scattered the contents of the asteroid belt far and wide. Embryonic planets were knocked out from their orbits. The building material of these planetesimals was thrown out and in towards the sun. Jupiter's charge displaced 99.9% of the material in this region of space, leaving Ceres half-formed, half-built, but with nothing more from which to grow. In this part of the solar system at least, the planetary construction business was shut down for good. How do we know such a dramatic turn in the solar system's history took place? The greatest evidence has come not from our own system, but from the study of other star systems and their planets, a field of science that has exploded in the last 30 years. Until the 20th century, the only evidence of how planetary systems formed and functioned came from one single source, Earth's solar system. Our own backyard was the one place that we had the technology to study, and that meant our view of how a planetary structure worked was deeply skewed towards the seemingly simple structure of a star at the center, 4 small rocky planets orbiting it, then a ring of millions of rocky pieces, remnants from its formation, followed by a series of 4 more planets, the gas giants. It has a pleasing, regular structure about it, all the rocky planets sitting close to the star and the gas giants orbiting further out. We supposed this must be the natural order of things, the way that solar systems have to form. But that all changed when the technology arrived to allow us to detect planets around distant stars. It soon became clear that our solar system is not typical at all. It may, in fact, be very odd indeed. In most of the planetary systems we've observed, the setup is remarkably different to our own. As we have extended our gaze and explored the structure around other stars with the help of exoplanet hunting technology like the extraordinary Kepler telescope, we've begun to see that one of the most commonplace categories of planet is completely missing from our own. Inward of Mercury, our solar system is essentially an empty void. But look at the equivalent region around most stars we have studied, and we often find it packed with a completely different class of planet, super-Earths. These worlds are between 2 and 8 times the mass of the Earth, with thick hydrogen-rich atmospheres. They sit incredibly close in to their stars, orbiting at a rate that makes the head spin. The first discovery of a super-Earth around a main sequence star like our own was made back in 2005 by a team led by Eugenio Riviera, using data from the Keck Observatory in Hawaii. Gliese 876d is an exoplanet almost 7 times the size of the Earth, which is orbiting just 3 million kilometers away from its red dwarf star, Gliese 876. Thought to be a rocky planet with surface temperatures estimated to approach 341 degrees Celsius, with an orbital period, year, of just under 2 days, this is a world completely inhospitable to life. To understand why this rocky planet is found so close in to the Sun, we need to understand the rest of the planetary system. And in the case of Gliese 876, that means looking at the 3 other planets circling further out from the star. The first of these planets to be discovered, and one of the earliest ever observations of an exoplanet, is 876b. Discovered in 1998 by the legendary planet hunter Jeff Marcy, we believe this world is a gas giant at least twice the size of Jupiter, but orbiting much closer to its parent star. In fact, at just 0.2 AU, 30 million kilometers, this massive planet is orbiting much closer in than Mercury orbits the Sun. At that distance, 876b zooms around on its orbit once every 61 days, compared with Jupiter's stately 12-year journey around the Sun. Either side of this giant planet are 2 other worlds, 876c, a gas giant 3/4 the size of Jupiter, and 876e, a planet we think is about the same size as Uranus. All 4 of these worlds orbit within a distance less than the orbit of Mercury. It's as if the whole planetary system has been squashed, packed in tightly around the star, and this configuration is far from rare. As we've explored more and more planetary systems, we've discovered this combination of super-Earths and close-orbiting gas giants is the nearest to a normal layout we observe. What underlies this is the fact that planetary systems are not the static and stable systems we had always assumed them to be. Far from the heavens being full of planets following eternal clockwork rhythms, most systems, including our own, are chaotic, dynamic, and turbulent. The reason for this is that, particularly early on in the infancy of a new system, planets frequently migrate, forming in one part of the system before wandering off into different zones. There are a number of different mechanisms behind these wanderings, but perhaps the most formative on the evolution of a planetary system is the Type 2 migration that occurs to gas giants early on in their lives. A gas giant planet like Gliese 876c would almost certainly have begun its life far further out than it is today, in a region more akin to where we see Jupiter or Saturn in our own solar system. At the very earliest stages of its existence, as this newly formed planet orbited within the cloud of gas and dust of its formation, the planet began to clear a path in its wake, and in doing so triggered a process that would transform its orbit. A shift in its gravitational interactions with the gas-rich disk would have slightly reduced its angular momentum and sent the planet on a different course, spiraling inwards towards the star at the center of the system. This seems to be a common path trodden by many gas giants around distant stars. and is the reason we find a preponderance of so-called hot Jupiters, massive gas giants sitting so close to a star that they orbit it in less than 10 days. The effects of these migrations have an impact far greater than just this, though. In ploughing inwards, a migrating gas giant like Gliese 876c ends up clearing vast areas of space, halting any planetary formation, and instead pushing material inwards towards the star, creating the perfect scenario for super-Earths like 876d to form. This cosmic pinball is the reason why so many of the planetary systems we've been able to explore follow the pattern of hot-ish Jupiter and super-Earths. But why not ours? What was different about the history of our solar system that led to the more expansive layout we see today? Scientists suspect the answer lies with our own gas giant, Jupiter, and the journey it took across the young solar system. The story of Jupiter begins not in the far reaches of the solar system, 778 million kilometers from the Sun, where it orbits today, but much closer in. We now think that almost 5 billion years ago, Jupiter formed around 520 million kilometers, 3.5 AU, from the Sun. At this time, the young giant was still surrounded by the disk of gas and dust from which it had arisen. But Jupiter began to slowly but surely clear its path through the cloud and debris. Over a relatively short period of time of just a few million years, the path through its orbit became completely clear, and just like the huge gas giants we've observed around alien stars like Gliese 876, this caused Jupiter to start spiraling inwards towards the Sun. This process was driven by the gravitational interaction between Jupiter and the cloud of gas, which, as it fell into the Sun itself, effectively dragged the planet with it. This was no subtle shift in Jupiter's orbit. While it spiraled inwards, it would keep falling closer and closer to the Sun, passing through the region of asteroid belt and robbing planetary hopefuls like Ceres and Vesta of the material they needed to complete the journey to planethood. But this was just the start of Jupiter's reign of terror. Further and further the young Jupiter fell, until it reached the vicinity of where Mars orbits today, just 225 million kilometers or so from the Sun. This was no quiet visitor to our local neighborhood. A planet of this size can wreak havoc just by its proximity, and Jupiter's arrival in the inner solar system did just that, transforming the destiny of many of the emerging new worlds, including our own. Lee Fletcher, from Jupiter Icy Moons Explorer mission, explains this action as a tug-of-war. Between the orbits of Mars and Jupiter, we have a large accumulation of objects, rocky objects mostly, known as the asteroid belt. They're not able to form and agglomerate into a complete planet because of the constant tug-of-war between the gravitational forces of the Sun and of Jupiter. So what we see today is a large disk of objects that could be the remnants left over from the formation of our solar system. To understand just how powerful a presence Jupiter must have been as it marauded around the inner solar system, we need to look no further than the worlds it has in its iron grip today. Jupiter has, at the time of writing, 79 known moons held in its orbit by the powerful gravitational field that is generated by the planet's enormous mass, a powerful force field that reaches out from the planet deep into the solar system. It's what has made Jupiter so destructive in the past, and through our exploration of the Jovian system, we have also witnessed its awesome power today. Nowhere is this power more dramatically revealed than on Io, the closest of all the moons to Jupiter. Io orbits just 350,000 kilometers from the cloud tops of its mother planet, a distance that makes it a gravitationally tortured world. A volcanic vision of hell, this is the most geologically active object in the solar system, with over 400 active volcanoes, from which lava flows stretch hundreds of kilometers across the moon's surface, and vast clouds of pyroclastic material blow hundreds of kilometers up into space, creating distinctive umbrella-shaped plumes above its surface. The surface of Io is perhaps the closest that our solar system has to offer of a vision of hell, and all of this activity is created not by ancient internal heat as we see on our planet Earth, but by the power and the influence of Jupiter's gravitational pull. Here on Earth, the volcanism that we see across our planet is driven by a combination of the heat that remains from our planet's violent formation and that which is released from the decay of radioactive elements locked away in the planet's interior. This heat, combined with the high pressures below the surface, creates the molten rock that pools within the mantle layer of the Earth, and then in certain places this magma finds a route to the surface, creating a volcano. On Io, the volcanism is nothing like this. Instead, it's being generated by a completely different mechanism, a process called tidal heating, that is driven in large part by its proximity to Jupiter and the gravitational tug-of-war between other nearby moons. Io is caught between the vast mass of Jupiter on one side and the three other Galilean moons, Europa, Ganymede, and Callisto, on the other, a dynamic that pulls in different directions to violent effect. It's a dynamic that we see in part on our planet every day, as the force of gravity flexes its muscles in the interaction between the Earth and the Moon, creating the twice-daily ebb and flow of our tides. On Earth, the gravitational tug of the Moon creates a tidal force that moves vast volumes of water around the planet, with the biggest difference between low and high tide creating a shift of a maximum of 12 meters in the height of water. The same principle also applies on the surface of the Moon, where the gravitational pull of the Earth creates tides not of water, but of rock. Moon tides are small changes in the height of rocks on the lunar surface caused by the pull of the Earth's gravity. In the case of the Earth-Moon system, these rock tides are measured in just a few centimeters, but Io tells a very different story. Io is roughly the same distance from Jupiter as our Moon is from Earth, and both moons are of equal size. But because Jupiter is so much more massive, the tidal forces it generates are much greater, with the gravitational pull of Jupiter moving the bulge of rock tides up to 100 meters between low and high tide. That's 5 times the height of any tide here on Earth, lifting the levels of solid rock up and down. In fact, Io contains the least amount of water of any known object in the solar system. But this is not the end of Io's torture. Its relationship with the other large moons, particularly the next moon out, Europa, also adds to the destructive forces that are pulling the very substance of Io apart. Io whips around Jupiter much quicker than our moon goes around the Earth, once again due to the mass of Jupiter, completing an orbit once every 42 hours. If left alone, Io would complete this orbit in a near-perfect circle around the giant planet. But Io is far from alone, and with Europa circling Jupiter precisely once every 2 orbits of Io, it means that in every second orbit, Europa and Io line up, and that rhythmic orbit has consequences. This is what's known as an orbital resonance, and the result is that it gives Io an additional gravitational kick that moves the moon's orbit out of a circle and into an ellipse. Ganymede is also in a resonant orbit with Io in a 1:4 orbital period ratio, and the outcome of this is that as Io orbits, the gravitational forces are constantly shifting and changing, and that stretches and squashes the moon, creating vast amounts of friction that causes its interior to heat up. It's a process called tidal heating, and it's this generation of heat that produces Io's volcanoes, raising the temperature in its interior to over 1,200 degrees Celsius, and creating the violent world of lava lakes and volcanic plumes that we've witnessed through the eyes of Galileo and Voyager. The pull of the 2 moons on Io also stops it gradually falling inwards to Jupiter and being completely ripped apart. Io is an extraordinary example of the power of Jupiter, and a demonstration of how this planet can shape and change the destiny of worlds. Because of its huge mass and the intense gravitational force this produces, any planet or moon that gets too close to it is under threat. While Earth is at a relatively safe distance today, 4.5 billion years ago, as Jupiter moved into the inner solar system, it began to exert its power right in the spot where Mars and our own world were beginning to form. 4.5 billion years ago, the region of the solar system we call home was densely packed with gas and rock, a planetary nursery full of embryonic worlds, each with a different destiny in store. But this fertile space was about to be thrown into chaos by the solar system's most unwelcome of visitors. As Jupiter was pulled from its distant orbit and continued its inwards descent, it paused in this planetary breeding ground. The consequences of this action would be significant and far-reaching. Detailed simulations of the impact this wandering Jupiter would have made suggest that the fate of any super-Earths caught in mid-formation would have been thrown into chaos. The models suggest that Jupiter's inward journey would have driven thousands upon thousands of planetesimals, many over 100 kilometers wide, spiraling into the inner solar system. This planetary breeding ground was turned into a battleground, as Jupiter's presence threw the orbits of any newly forming super-Earths into the overlapping paths of thousands of massive blocks of rock and ice. The result was carnage, a cascade of collisions that blew apart planets and left a trail of fragmentary worlds in its wake, a chain reaction that would culminate in the formation of a spiraling swirl of gas, dust, and rock that would have swept any surviving super-Earths towards the Sun and ultimately to their destruction. In what was just a fleeting moment in the history of our solar system, its destiny changed forever. Our planet would not fit the norm of super-Earths and the tightly packed gas giants that we see across the Milky Way. Instead, we think the inner solar system would have been swept clear of up to 90% of the rocky material thrown in by Jupiter. With just crumbs remaining, 4 small terrestrial planets began to form from the rubble. With Jupiter marauding in its orbit, much of the material that could have gone on to form Mars was lost, leaving the planet with enough scraps to make a planet half its potential size, and transforming it from a possible habitat for life to a world that would freeze and die in its adolescence. Just that little bit further in, Earth found itself forming in a slightly more substantial ring of gas and dust that would make it the largest of all the terrestrial planets. A lucky escape for our future home, because had Jupiter continued on its inward path, Earth might never have formed at all. But just as it looked like it would sweep everything away, Jupiter stopped in its tracks. On its inward journey, Jupiter had transformed the inner solar system, sweeping away the formative giant planets and leaving just enough material for Mars, Earth, Venus, and Mercury to form. But the stage was now set for another player to enter the story and shift the destiny of both our world and the solar system once again. Waiting in the shadows of the outer solar system, another massive planet was lurking that we now think pulled Jupiter back from the brink. Saturn, a gas giant not as big as Jupiter, but enormous nonetheless, began its own slow drift inwards towards the Sun. Formed much further out than Jupiter, as Saturn began turning inwards, it would have a profound effect on Jupiter's trajectory. As the two giants drew closer together, they became locked in an intimate gravitational dance, an orbital resonance that meant that for every orbit Saturn made around the Sun, Jupiter made 2 circuits, exerting a regular periodic gravitational influence on each other as the two giant worlds passed close by. The result of this orbital resonance between Jupiter and Saturn cleared out all of the gas and dust between the 2 planets, creating a gap in the disk of the early solar system. And this interaction between the 2 resonant planets and the gas and dust at the edge of the gap resulted in both planets changing tack. The orbits of both Saturn and Jupiter began to move outwards, away from the Sun, preventing Jupiter from moving any further into the inner solar system. Earth was given a reprieve, and Jupiter was dragged back out into the asteroid belt once more. This change in direction has become known as the Grand Tack Hypothesis, a nod to the action of a sailboat as it tacks and changes course while it travels against the direction of the wind. Just like a sailboat, the theory suggests Jupiter tacked around 1.5 AU from the Sun, in the current orbit of Mars, changing direction and pulling back out to its current orbit at 5.2 AU. It's a theory that's been driven by using advanced computer modeling, which helps to explain many of the inconsistencies between our solar system and the hundreds of other planetary systems we've recently observed. It's the grand tack that accounts for the lack of super-Earths and explains the presence of only a handful of small rocky worlds with thinner atmospheres than those observed around other stars. The grand tack also allows us to explain the unusually small size of Mars, which simulations predict should be at least half the mass of the Earth, if not bigger, rather than the 0.107 Earth's mass we find it to be. It also helps explain the odd inhabitants of the asteroid belt, transformed by Jupiter's journey not just once but twice across this region of space. This is why we see half-finished planets like Ceres and Vesta left starved of building material, and an asteroid belt that has a surprisingly small mass, with objects that appear to originate from both inside and outside Jupiter's orbit, and have a wide range of eccentric orbits themselves. Jupiter, the father of the skies and ruler of the heavens, had spread its hand far and wide, sculpting the precious solar system we see today in the space of just a few million years. Before coming to rest, though, it would grant one more precious gift to the newly forming planet Earth. As Jupiter was dragged out, crossing the asteroid belt for a second time, it encountered a region full of objects rich in water and bearing minerals, and Jupiter's trajectory caused these objects to be flung back into the inner solar system. They crashed into the young planets and moons with an intensity never seen before or since, in a period known as the Late Heavy Bombardment. It transformed the makeup of the inner solar system, delivering a large percentage of the water Earth holds on its surface today. It's extraordinary to think that it was Jupiter that was responsible for the delivery of the most important ingredient of life, the water that provided an ideal environment for life to spark and thrive in one unbroken line for the last 4 billion years. This story offers an extraordinary understanding of the power Jupiter has wielded over all of our lives. The more we learn about the formation of solar systems, and the more we try to model a system like ours with 4 terrestrial, water-rich planets close to the star and the gas giants further out, the more we learn that perhaps all these things had to happen. These unlikely movements and interactions between the planets were necessary to produce a system like ours, and a planet like ours. So if events like the tack of Jupiter are, as we believe them to be, extremely uncommon, the conditions for the formation of Earth-like planets, terrestrial worlds with plenty of liquid water beneath the gentle pressures of a thin blue line, must be exceedingly uncommon. It's a humbling thought to begin to comprehend that the Earth may not just be a rare rock in our solar system, but a rock that only exists because of the rare system of planets within which it evolved. All the evidence is beginning to suggest that we may be living on a tiny oasis within a vast desert, devoid of life and stretching out across the Milky Way. Today, Jupiter has settled into a regular orbit at the far side of the asteroid belt, its days of marauding through the solar system at an end. Established in a stable orbit for almost 4 billion years, it has looked down on our planet as a distant light in the sky, unchanging while the work of evolution by natural selection has transformed the first sparks of life on Earth into the endless, beautiful forms that we witness today. But although distant and seemingly detached, Jupiter's influence has been far from benign. The history of life on Earth has been interrupted by numerous cataclysms, impacts with asteroids that have fundamentally shifted life again and again. And the hand behind these disruptions? It's Jupiter, that has continued to hold immense sway over our planet, exerting its influence on the asteroid belt with just the smallest of nudges, the difference between existence and extinction. At 16:53 UTC on the 18th of October 1989, the Space Shuttle Atlantis took off from the Kennedy Space Center in Florida, carrying the Galileo spacecraft carefully packed away in its hold. Released into Earth's orbit from the cargo bay just a few hours later, the probe would begin a 6-year journey to Jupiter that would utilize flybys of Earth and Venus to propel it on its 4.6 million kilometer voyage across the solar system. Entering orbit around the giant planet on the 8th of December 1995, Galileo would not only become the first spacecraft to orbit Jupiter, but also the first craft to orbit any of the outer planets. It spent nearly 8 years in the Jovian system and explored the giant planet and its menagerie of moons in intricate detail for the very first time, revealing a host of new discoveries. From precise measurements of Jupiter's atmosphere and observation of its giant thunderstorms, to discovering liquid water under the surface of the moon Europa and the first detailed studies of the intense volcanic activity of Io, this was a mission that opened our eyes to the beauty and diversity of the Jovian system, in a level of detail that we could scarcely have imagined possible. But long before Galileo even arrived, this 2-ton explorer would already have changed our view of the solar system. Entering the asteroid belt in August 1991, Galileo performed the first close-up flyby of an asteroid, passing within 1,500 kilometers of 951 Gaspra, and returning the first detailed images of this rocky remnant back to Earth. Its next close encounter would come almost 2 years later, when flying past 243 Ida, the probe discovered that this asteroid had its own moon. Dactyl, as it has become known, was the first asteroid moon ever to be discovered, and the images are beautiful. A tiny 1.5-kilometer wide object in a chaotic orbit around its parent rock. After this unexpected encounter, Galileo continued its long journey across millions of kilometers of empty space, still 4 years away from its ultimate rendezvous with Jupiter. But by luck rather than judgment, this tiny probe happened to be traveling towards Jupiter at the precise moment it would be able to witness one of the rarest of shows our solar system has to offer. On the night of the 24th of March 1993, as Galileo sped across the solar system, 3 astronomers working at the Palomar Observatory in California were attempting to spot and track what are known as near-Earth objects, undetected meteors that might be of potential threat to our planet. That evening, David Levy, along with Carolyn and Eugene Shoemaker, took a series of images using the 1.5-foot Schmidt telescope. Lurking in one of them was an unusual artifact that grabbed the attention of the team. Streaking across the image was an object that, although nowhere near the Earth, was of immediate and immense interest. A comet that appeared not only to be unusually close to Jupiter, but also seemed to have multiple nuclei, a fragmented series of rocks trailing across 1 million kilometers of space. In a moment of wondrous astronomical serendipity, the team had discovered the first ever comet in orbit around another planet. A comet that had not only been captured by Jupiter's immense gravity, but had also been pulled apart by it. Shoemaker-Levy 9, as it became known, because it was the 9th comet this team had found, was a comet unlike anything we'd seen before. Quickly confirmed by further studies to be orbiting Jupiter, and thought to have been captured from its solar orbit back in the late 1960s or early 1970s, astronomers were able to wind back through its orbital history and calculate the precise moment the comet was ripped apart. Passing just over 40,000 kilometers above Jupiter's cloud tops on the 7th of July 1992, we think Shoemaker-Levy 9 fell within the planet's Roche limit, and this 5-kilometer comet was ripped apart by the huge tidal forces generated this close to the planet. It disintegrated into 23 pieces visible to us here on Earth, labeled fragments A to W, with the biggest up to 2 kilometers in diameter. This alone was a remarkable discovery, a visual representation of Jupiter's colossal gravitational power. But if that wasn't enough, it quickly emerged from orbital calculations that the comet seemed to be on a trajectory that would ultimately take it straight through the center of the planet. Shoemaker-Levy 9 was on a collision course with Jupiter, and as if we had scheduled it ourselves, the date of the predicted impact was July 1994. Perfect timing for the spacecraft we already had en route. By the beginning of July 1994, Galileo was 238 million kilometers from Jupiter, on the very edge of the asteroid belt and speeding through space towards its final destination. Ahead of it, comet Shoemaker-Levy 9 was entering its final few days in orbit around the planet. With the first impact expected on the 16th of July, the world's most powerful terrestrial telescopes were trained here, as well as some of our space observatories, from the newly fixed Hubble Space Telescope to the Ulysses spacecraft, which turned its gaze from its primary job of watching the Sun. Even the distant Voyager 2 probe, 6.6 billion kilometers away beyond Neptune, was able to look for radio wave emissions from the impact and employ its ultraviolet spectrometer to make distant observations. But for all of this technology peering across the solar system, there was only one set of eyes that would be able to see the actual first impact. The comet would first hit Jupiter on the side turned away from the Earth, but Galileo was approaching on the night side of the planet, which would give us a unique view, not visible from Earth, of our first ever observation of a collision between two objects in the solar system. The first impact occurred at 2013 UTC on the 16th of July, when fragment A entered Jupiter's southern hemisphere traveling at 60 kilometers a second, hitting the planet with an estimated force of 300 million atomic bombs. With its instruments trained on the impact, Galileo recorded the subsequent fireball, which reached temperatures of over 24,000 degrees Kelvin, creating huge plumes that stretched over 3,000 kilometers high. It was a breathtaking spectacle that quickly came into view from Earth as the rapid rotation of Jupiter brought the impact sites into clear sight, revealing a huge, dark spot on the surface. Over the next 6 days, 21 distinct impacts were observed, as each of the fragments impacted with its own distinct set of characteristics. Fragment G was the largest of all the impacts. Striking Jupiter on the 18th of July, it created a vast scar on the surface of the planet, stretching over 12,000 kilometers across. This extraordinary spectacle continued until the 22nd of July, when Fragment W brought the show to a close, leaving just the scars of the impacts to slowly fade away over the following months. Galileo had given us a ringside seat for this rarest of phenomena. Aided by our technological eyes and ears on Earth and across the solar system, we were able not only to witness a collision like this for the very first time, but also to harvest a vast amount of data. It transformed our understanding of the composition and atmospheric dynamics of Jupiter, allowed us to precisely measure the actual size and composition of the comet itself. But perhaps most important of all, it enabled us to study a cosmic collision firsthand, revealing one of the most important dynamics of Jupiter and the power it exerts over every object and planet in the solar system, including Earth. Before it fragmented, Shoemaker-Levy 9 was at least 2 kilometers wide and weighed over 800 million tons, traveling through the solar system in an orbit that would have taken it hurtling through the inner terrestrial planets, and perhaps even close to Earth. If such an object had hit us, the consequences would have been devastating, sending a vast amount of dust and debris into the air, creating a global smog that would have darkened the planet and cooled the atmosphere, leading to a catastrophic impact on all life on Earth. We will never know whether Shoemaker-Levy would have posed a real danger to our planet, but we do know that Jupiter removed the threat, and such acts of planetary protection are not unusual. The impact of this comet demonstrated in spectacular fashion the role of Jupiter as a cosmic vacuum cleaner. Using its vast gravitational power to capture objects like SL9, by bringing them into its orbit and incinerating them on impact, we think Jupiter acts as the grand protector, luring in objects that might otherwise pose a threat of collision with the Earth. But as we have so often seen with the story of Jupiter, no act is ever truly benevolent. For every potentially dangerous object it shields us from, it can throw another in our direction. That's because of the influence it exerts over all the objects in the asteroid belt. It's easy and quite natural to think of the asteroid belt as a single homogeneous structure, a ring of rocks orbiting in an orderly fashion around the Sun. But it's nothing like that at all. In reality, each of the millions and millions of pieces of rock is following its own individual orbit, distorted and eccentric orbits that create what appears to be a chaotic cavalcade around the Sun. But although there are complex patterns, there is also structure, and nothing has more influence on that structure than Jupiter, the silent conductor of the asteroid belt. In some way, every asteroid dances to Jupiter's tune, whether it's the Trojan asteroids orbiting ahead of and behind Jupiter, or the Hilda asteroids that orbit around in 3 groups, due to the delicate interplay between the gravitational pull of the Sun and that of Jupiter. Every asteroid is in some way caught between the 2 largest objects in the solar system. In such a chaotic, complex system, collisions between asteroids are inevitable, and disturbances to an orbit are commonplace. All it takes is for an asteroid to line up with Jupiter, and the resultant gravitational kick it receives can send an asteroid hurtling outwards, banishing it to the far edges of the solar system, or inwards towards the inner planets. It's by this mechanism that Jupiter continues to exert its influence across every corner of the solar system. Over the last 4 billion years, from its distant orbit 778 million kilometers away from the Sun, Jupiter has repeatedly played with the destiny of our planet and the path of life upon it. The surface of the Earth is strewn with the evidence of cataclysmic collisions that have significantly shaped the history of the planet, from the delivery of huge volumes of water almost 4.5 billion years ago, to the near planet-destroying events of the late heavy bombardment, and even the formation of the Earth-Moon system. All of these momentous events can be linked to the shifting influence of Jupiter and its gravitational stranglehold on objects across the solar system. Over millions of years, the evidence for many of these collisions has been lost or hidden under the ever-changing surface of our planet. But as we've been able to see at impact sites like the Barringer crater, Jupiter's hand is never far away from shaping events on the surface of Earth. The discovery of one such impact crater underneath the Yucatan Peninsula in Mexico back in the late 1970s has revealed evidence of an event that in a single moment changed the course of life on Earth perhaps more profoundly than any other, transforming the very possibility of our own existence. Around 66 million years ago, in the far reaches of the asteroid belt, an object at least 15 kilometers wide was making its final orbit of the Sun. Just one asteroid among millions, this insignificant object had been following the same path for millions, if not billions of years. But then, something changed. Exactly what caused it to alter its path will never be known. But the most likely explanation is that a gravitational nudge from Jupiter pulled it out of its innocuous orbit and sent it on a very different trajectory, a direction that would ultimately bring it on a collision course with Earth. Traveling through space, it would have descended through our atmosphere in just a few seconds, before striking the Earth with a force equivalent to 100 million megatons of TNT. The impact generated a fireball so hot that anything within a 1,000-kilometer radius was instantly vaporized, leaving a crater 180 kilometers wide and 20 kilometers deep. Today, the town of Chicxulub sits near to what we think is the center of the impact site, and lends its name to the crater that stretches out west onto the Yucatan Peninsula and east into the Gulf of Mexico. The evidence for this giant impact doesn't just sit in the partially hidden Chicxulub crater, but also in a thin layer of sediment found throughout the world that contains unusually high levels of iridium. This metal is exceptionally rare in the Earth's crust, but is found in abundance within asteroids. So we believe its presence in the thin layer of sedimentary rocks around the globe dating back 66 million years ago is a direct remnant of the huge rock that struck the Earth. This geological signature is known as the KPG boundary because it marks not just the impact itself, but a boundary between 2 epochs of life on Earth, the end of the Cretaceous period and the beginning of the Paleogene. It was an event that lasted just a few seconds, but in the aftermath of the impact, millions of tons of sulfurous rock were thrown up into the atmosphere, and during the nuclear winter that followed, 75% of all species were wiped from the face of the Earth, including the largest creatures ever to walk the planet. In a global extinction event that affected every continent simultaneously, the age of the lizards was brought to an end, as almost every species of dinosaur, and many other species as well, vanished in the space. According to Steve Desch, professor of Earth and Space Exploration at Arizona State University, it was an event we would not like to see the likes of again. If something the size of the Chicxulub impactor that killed the dinosaurs were to happen today, it would just be utterly catastrophic for mankind. The most immediate thing is you would have a magnitude 13 earthquake, and then you would have tidal waves that could happen anywhere near water that are miles high, propagating out for thousands of miles in every direction, and that's just for starters. Eventually, so much dust would be kicked up into the atmosphere, it would block sunlight, destroy agriculture, our infrastructure would fail. Today, just traces of the dinosaurs remain. These creatures that ruled the Earth are now nothing more than a dusty history captured in the fossil record. One event, one asteroid, one orbit that was changed by the might of Jupiter. Without the distant planet's intervention, it's possible that those giant lizards might still be here today, and the evolutionary niche that opened up for us with their removal might never have appeared. There are many chance events, not only throughout the history of Earth, but also spanning the entire history of the universe for 13.8 billion years, without which we wouldn't exist. There's an unbroken chain of life stretching back 4 billion years here on this planet. But having said that, there are major events that affected life, and one of them, without doubt, is the asteroid that wiped out the dinosaurs. And so, in that sense, it is true to say that without Jupiter, we wouldn't be here. The godfather of the planets paved the way for humankind to inherit the Earth, and it has looked down on us benevolently ever since, using its immense power to keep us safe. A sleeping giant with its power undiminished. An asteroid impact like the one that cleared the way for us to evolve 65 million years ago would have catastrophic consequences for our civilization, were something similar to strike today. To the naked eye, Jupiter is one of the brightest points of light in the night sky, and through a small telescope it is a beautiful, banded world. It feels distant, eternal, disconnected from events here on Earth. But the more we've learnt about the history of the solar system, the more we've come to understand that that is not the case. Jupiter has played an important and perhaps decisive role in the stories of all the planets, including Earth. You see, the solar system is just that. It's a system, complex, interconnected, and interdependent. So the next time you see Jupiter, just hold your gaze and think for a while about the fact that it is so much more than a point of light, or a planet even. Jupiter is the great sculptor of the solar system, the destroyer and creator of worlds. Saturn is a gas giant, alive with storms of unimaginable ferocity, a world of alien weather where diamonds rain down from the sky, and bubbling vortexes whip around the planet so fast they catch up with their own tails. And glistening in the distant light of the sun is a 500,000-mile ring of almost pure frozen water, broken into millions of individual pieces. This structure is unique in our solar system, sculpted by the delicate hand of gravity. Yet for all of their iconic beauty, the rings are just a fleeting shadow, an echo of Saturn's past, and an ephemeral structure that has adorned the planet for a brief moment in its history and will soon disappear again. Saturn is a place of many worlds, encircled by at least 62 moons. This menagerie of satellites boasts worlds of astonishing variety. Titan, bigger than the planet Mercury, is the only moon in the solar system to have its own substantial atmosphere, while Mimas is the smallest body in the solar system. Perhaps most astonishing of all, though, is Enceladus, an ice moon with an ocean of liquid water inside that seems to contain all the building blocks of life. Composed of 96% hydrogen and 3% helium, Saturn has a diameter at its equator almost 10 times the size of the Earth, at 120,536 kilometers. Its volume would hold 800 Earths. However, with a mass made up predominantly of gas, the planet's density is remarkably low. As the only planet in the solar system less dense than water, if you could find a bathtub big enough to hold it, Saturn would literally float in it. Beneath the frosty -178 degrees Celsius cloud tops, the pressure rapidly increases under the huge weight of Saturn's dense atmosphere. The hydrogen gas of the upper layers turns at first into liquid, and then, hundreds of kilometers further below the planet's cloud tops, into slushy metallic oceans of hydrogen. We can only make an educated guess about the structures that lie within Saturn's unreachable core. With temperatures at its center exceeding 11,000 degrees Celsius, Saturn generates far more heat from within itself than it receives from a sun that sits on average 1.4 billion kilometers away, meaning that it must be generating its own heat. With such extreme temperatures and pressures, the structural makeup of this planet is uncertain and hotly debated. According to planetary scientist and physicist Jonathan Lenine, if you go down, down, down through the hydrogen, through the helium rain to this core of rocky and icy material, it's not rock and ice. It's some sort of atomic crystal where the elements of rocks and ice, the silicon, the oxygen, the magnesium, are all together in a structure that doesn't exist in the rocks on the Earth. Now, in the case of Jupiter, it might actually be warm enough that the core is a liquid, that it's molten. In the case of Saturn, it's probably a solid core, but definitely an exotic one. Undoubtedly, there is a dense core at the heart of Saturn, one that is almost certainly composed of iron-nickel alloy and rocky silicon-based compounds. But exactly how this material behaves at such extremes remains a mystery. From its surface all the way down to its center, Saturn is a world of mystery. This gas giant, along with its sister planet Jupiter, is worlds apart in character from Mercury, Venus, Earth and Mars, the terrestrial planets of the inner solar system. It's hard to imagine how they could all have been created from the same ingredients, the singular cloud of gas and dust that gave birth to every planet in our solar system. But if we go back far enough in time, we begin to uncover a history with a surprisingly familiar origin. The beginning of Saturn's story is far more recognizable than its present-day character would suggest, because at the heart of all the ringed planet's beauty lies a lost world, a primordial one that disappeared from view billions of years ago, and yet was the seed for everything that Saturn was to become. Without this early world, there would have been no gas giant, no rings of ice, and no hope of an orbiting oasis of life in the far distant reaches of our solar system. The story of Saturn, like that of all the planets, began around 4.5 billion years ago. In the light of the awakening sun, a vast cloud of gas and dust swirled around our newly formed star, and that protoplanetary disk of gas and dust clumped and coalesced until it slowly began to form into a collection of embryonic worlds that would go on to become the 4 rocky planets sitting closest to the sun. Millions of kilometers further out, in the cold, distant reaches of the solar system, a similar story was playing out, but this tale of planetary formation would follow a very different path. That's because Saturn was molded beyond a boundary called the ice line, sometimes also called the snow line, which is a frontier that marks the divide between the terrestrial planets and the gas giants. Respective proximity to this line would lead the evolution of Saturn and that of its neighboring planet Jupiter to play out very differently. The ice line, as you might expect from the name, is a way of dividing a solar system into 2 broad zones based on temperature. Inside the ice line, the strength of a star is strong enough to keep things pretty warm. But step onto the other side of the line, and you've crossed a boundary where it becomes cold enough for volatile compounds like water, methane, ammonia and carbon dioxide to condense and freeze solid. Each of these compounds does, of course, have its own precise ice line due to the different specific freezing points of each individual compound. But beyond a certain point, the boundary begins to incorporate the freezing points of a large number of compounds. Today, the ice line is thought to be around 5 AU. That's around 750 million kilometers from the Sun, which means it lies well beyond the asteroid belt, at a distance just before the orbit of Jupiter. But in the infant days of the solar system, that distance would have been much less. With a weak, young sun shrouded in an opaque cloud of dust and gas, the early ice line would have fallen about 2.7 AU from the sun, smack bang in the middle of where we find the asteroid belt today. We know this because we've been able to explore the makeup of the asteroids on either side of this line. Beyond the 2.7 AU line, we've discovered the asteroids to be icy objects with large amounts of water ice locked away within them, while on the inside of this line, we find a very different class of asteroid, dry and largely devoid of water. It seems these bodies formed in a region of space that was simply too warm to allow substantial amounts of ice to exist. Why does the ice line matter in the story of Saturn's evolution? In the early solar system, as the protoplanetary disk swirled around the young sun, the ice line not only defined an important boundary in terms of temperature, but it also created a dramatic difference in the abundance of material available to build a planet on either side of the line. Beyond the ice line, the lower temperatures meant that all of those frozen volatile compounds were swirling around in the cloud of gas as solid grains, building blocks that provided vast amounts of additional material to feed into the process of planetary accretion. And the impact of this simple physical difference was profound. On our side of the line, we find only rocky planets like Earth, Venus, and Mars, while on the other side of the line, there is not a single planet that we recognize as terrestrial, just the gas giants of Saturn and Jupiter, and the ice giants of Uranus and Neptune beyond. To understand the reason for this stark delineation, we need to look back to a critical time in Saturn's history, to the moment where the paths of the planets either side of this ice line began to diverge. Saturn began its life not as a beautiful jewel, but as a tiny, ugly, ragged world. Just like its terrestrial cousins, the origins of this gas giant planet began with the clumping together of tiny specks of gas and dust that slowly grew into bigger and bigger clusters. As this embryonic new world tumbled wildly through space, days would have lasted minutes as the distant sun lit its twisted surface, rising and falling in chaotic rhythm repeatedly. Eventually, as it grew, this ragged rock began to transform itself, taking the new shape of a spherical world as it went from planetesimal to protoplanet. On the warm side of the ice line, the growth of the terrestrial planets came to an abrupt halt. As these planets had secured stable orbits and began clearing their way through the protoplanetary disk, the supply of raw ingredients ran dry, and so their growth simply stopped, starting with the runt of the litter Mars, followed by Venus, and then our planet Earth, the largest of the rocky planets. But on the other side of the ice line, it was a very different story. With no shortage of building material, the growth of the protoplanetary Saturn was able to progress at a rapid rate. With abundant amounts of rock and ice, the young Saturn continued to grow, quickly dwarfing any of the terrestrial planets that were forming in the far distant glow of the warming sun. Over a relatively short period of hundreds of thousands of years, this plentiful supply of material smashed and clumped and grew until, through a series of planetary-scale collisions, Saturn became the largest object for millions of miles in any direction. The bigger it got, the stronger its gravitational field grew, and so it could attract ever more material into its grasp. Eventually, the violence of its early life allowed Saturn to grow into one of the biggest worlds of rock and ice the solar system had ever seen. What did this world look like? We simply do not know. The detail of how any of the planets formed in the solar system is only sparingly understood. These are events that happened 4.5 billion years ago, and it's very much still cutting-edge scientific research trying to piece together the barest of timelines, let alone the intricate details of these distant events. Much of what we do understand of the evolution of our own solar system and the planets within it has been supported by our recent ability to study worlds outside it in neighboring systems. The study of exoplanets has allowed us for the first time to peer into the evolution of other star systems and witness the formation of hundreds of different planets rather than the 8 in our own backyard. Much of this evidence supports the idea that Saturn was once a world of rock and ice, a world that grew to perhaps 10 or even 20 times the mass of the Earth as it gorged itself on the available matter. This was a world we would at least have vaguely recognized, a place it is almost possible to imagine, a world that you could stand on and survey. But it was a world that wouldn't last. The fact that Saturn grew to such a size had significance beyond just scale. Its size pushed the planet towards a very different evolution, changing its relationship with the environment and ultimately sending it on a completely new path. It's because of its immense mass and its place in the solar system that Saturn wouldn't remain a rocky world for long. The history of the exploration of Saturn is littered with many of the greatest names in the field of science. Galileo Galilei was the first to peer at her through a telescope in 1610, mistaking the faint outline of the rings for two moons on either side of the planet. He famously reported the planet appeared to have ears. 2 years later, however, when he looked up again, the peculiar structures on either side of the planet had disappeared. We now know this is because the rings were facing the Earth edge-on at the time of observation. But for Galileo, this was a strange and mysterious anomaly. It would take almost 50 years and the more powerful telescope technology of Christian Huygens to solve the problem. Using a 50mm refracting telescope, Huygens was the first to spot a moon of Saturn, publishing his discovery of Titan in 1656. At the same time, his observations led him to begin formulating a theory to explain the strange ears that Galileo had first seen. Not moons, but a ring around the planet. Uncertain that he had enough proof to convince the scientific community of his hypothesis, Huygens did what was common at the time. He published his thinking not as a preliminary hypothesis, or even as a line of investigation, but instead, in order to mark the territory and protect his reputation, he announced his discovery in the form of an anagram. A C C C C C D E E E E E G H I L L L L M M N N N N N N N N N O O O O P P Q R R S T T T T T U U U U U. For 2 years the anagram remained unbroken, protecting Huygens' claim to be the first to identify the rings, while also giving him enough time to build the evidence to make the hypothesis defendable. It wasn't until 1658 that Huygens revealed the meaning of the anagram to be a Latin sentence: Annulo cingitur tenui, plano, nusquam cohaerente ad eclipticam inclinato, which means, it is surrounded by a ring, thin and flat, never touching, oblique in relation to the ecliptic. With the rearrangement of 62 letters, one of the most beautiful structures in the solar system, the rings of Saturn, had been revealed to the world, if not yet understood. While Giovanni Cassini and William Herschel went on to discover more moons of Saturn and to detail structures within the rings, including the 4,800-kilometer gap between the A and B ring that would later become known as the Cassini division, we still imagined the rings as one great disk, a flat, solid circle of material encircling the planet within. It was Pierre-Simon Laplace, the French Newton, who was the first to suggest in 1787 that such a singular structure around a planet would be unstable, and instead was more likely to be comprised of a number of solid ringlets. By the mid-19th century, it was the turn of the great mind of James Clerk Maxwell to investigate the rings. Unpicking centuries of conjecture around the nature of the rings, he demonstrated for the first time through a series of mathematical proofs that any solid structure, be it single ring or ringlets, would be unstable and so unable to exist around the distant planet. Therefore, Maxwell concluded, the rings must be composed of a huge number of small particles, all orbiting the planet independently. In his words, every particle of the ring is now to be regarded as a satellite of Saturn, disturbed by the attraction of a ring of satellites at the same mean distance from the planet, each of which, however, is subject to slight displacements. The mutual action of the parts of the ring will be so small compared with the attraction of the planet that no part of the ring can ever cease to move round Saturn as a satellite. With Maxwell's publication on the stability of the motion of Saturn's rings in 1859, our modern understanding of this distinctive feature of Saturn had begun. But it would be another 120 years before we'd get the chance to explore the most remarkable bodies in the heavens, as Maxwell described them, up close. At 14:26 Universal Time on the 1st of September 1979, after a 6-year journey from Cape Canaveral across over 1 billion kilometers of space, the Pioneer 11 spacecraft took us within touching distance of the rings of Saturn for the very first time. As our first explorer to cross the boundary of the rings, Pioneer flew across the ring plane beyond the outer ring, enabling it to photograph the Saturnian system in extraordinary detail, sending back a series of images that revealed the ringed planet in greater resolution than we could ever have seen from Earth-bound observations. On its way through the ring plane, Pioneer was able to take the first close-up measurements of the rings, and in doing so discovered not only a new ring system, the F ring, but also 2 new moons of Saturn. In fact, the spacecraft flew so close to the as then unknown moon, passing at a distance of just 6,676 kilometers, it was lucky the mission didn't abruptly end with a massive collision. We now know Pioneer had encountered either Epimetheus or Janus, but we're still not sure which one of these 2 similar-sized moons it was, as both sit in the same orbit around Saturn. Traveling at a speed of 114,100 kilometers per hour, Pioneer passed within 21,000 kilometers of Saturn's cloud tops, making its closest encounter at 16:29 UST on that September day, before speeding off beyond the rings and onwards on its journey to the outer solar system. As well as taking 440 images of the Saturnian system, Pioneer measured the characteristics of Saturn directly. An array of sensors were able to confirm that this giant planet was a bitterly cold world, with an average overall temperature of minus 180 degrees Celsius, and a composition made up almost entirely of liquid hydrogen. But beyond the basic data, perhaps Pioneer's greatest achievement was to plot a course through the Saturnian system and make its way safely through the ring system while returning data back to Earth. Now the stage was set for the 2 Voyager probes, already well on their way across space, speeding towards the ringed planet equipped with an even more advanced array of technology, ready to probe even deeper into Saturn's mysteries. The rings were named essentially in order of discovery. In terms of the main rings, it starts at the outermost, which is the A ring, and then goes into B ring, where most of the mass is. And there's a faint C ring and an even fainter D ring inside that. Then the E ring was discovered around 1980, when the rings as viewed from the Earth were edge-on. That's the one that's clearly associated with Enceladus. Then Pioneer 11 discovered the F ring, and then Voyager discovered the G ring. And the G ring, we know, is associated with a moon called Aegeon, which is the source material for the ring. At that stage, we stopped using the letters as a nomenclature. So there are other individual rings that have been named, but they tend to be rings or ringlets that are in the main ring system itself. Carl Murray, Cassini mission, on the organization of Saturn's rings. Just over a year after Pioneer had exited the Saturnian system, early in November 1980, Voyager 1 swept in with its high-definition cameras primed and ready for action. As it sped past Saturn at 17 kilometers per second, it was able to produce a wealth of new data about the planet, rings, and moons. One of its key discoveries was the identification of 3 new moons, Prometheus, Pandora, and Atlas. The mission revealed detailed relationships between these moons and the ring system within which they sat, which also confirmed a long-standing theory about the structure of the rings. At least the first 2 of these moons are shepherding moons, satellites that exist within the narrowest rings of Saturn and play an essential role in keeping the delicate structures in place by their gravitational interactions with the billions of particles within the rings. With its wide and narrow-angle cameras, Voyager 1 was able to take a series of pictures showing in incredible detail Prometheus acting as a shepherding moon to the F ring and Atlas as a shepherd to the A ring. This first Voyager craft was also sent by the team at NASA's Jet Propulsion Laboratory to investigate one of Saturn's most intriguing moons up close, for the very first time. Titan had already been identified as potentially the only moon in the solar system with a thick Earth-like atmosphere, and Voyager was set on a course that enabled it to pass by within just 6,400 kilometers of its surface. As it flew on the dark side of the moon, looking back at Titan's atmosphere through the haloed light of the sun, it was able to accurately measure for the first time the density, composition, and temperature of the atmosphere, and also obtain a precise measurement of Titan's mass. This mysterious moon, the largest of all Saturn's satellites, was found to have an atmosphere almost entirely composed of nitrogen, just like the Earth, with a surface pressure just 1.6 times that of our planet. Voyager opened our eyes to this curious world for the first time, a world we would come to explore in even more detail with the Cassini-Huygens mission, which would touch down on the surface of Titan. As well as exploring the rings and moon systems of Saturn, Voyager 1 was able to deploy its array of sensors and cameras on the planet itself. With its closest approach on the 12th of November 1980, Voyager came within 77,000 miles of the Saturnian cloud tops, and was able to measure powerful winds traveling at 1,100 miles per hour, whipping around the planet's equator and aurora. But most intriguing of all was the discovery that Saturn's upper atmosphere was composed of only 7% helium, while the rest was mostly made up of hydrogen. Scientists had expected Saturn to have the same atmospheric helium levels as Jupiter and the Sun at 11%. So this much lower level suggested something intriguing was going on deep within Saturn's internal structures. Where was the missing helium? The lower levels in Saturn's upper atmosphere suggested that the heavier helium might be slowly sinking through Saturn's hydrogen, but it would take the arrival of Voyager 1's sister craft 9 months later to enable scientists to further probe the inner workings of Saturn, and to begin to reveal the fate of the rocky ice world that had been lost inside this planet billions of years earlier. While passing behind Saturn, and so shielded from the view of the Earth, Voyager 2 used its radio science system to probe Saturn's upper atmosphere, gathering information on its atmospheric temperature and density. It was an ingenious dual use of its telecommunications system that allowed Voyager to create a temperature profile of the planet that provided the first direct evidence of something that scientists had long suspected. At the uppermost level of its atmosphere, Saturn's temperature was 70 K, minus 203 degrees C, while at the deepest levels, around 120 kilopascals, the temperature increased to 143 K, minus 130 C. Saturn, it seemed, was emanating far more heat than it was receiving from the Sun. This was a planet with a mystery at its heart, but Voyager was about to gain an even more beguiling insight into Saturn's inner workings. In August 1981, as the Voyager 2 probe passed over the north pole of the planet, it took a series of images with its 2 camera imaging systems that would reveal an extraordinary secret sitting on Saturn's crown. Stitching together the images and analyzing the data from this distant probe, David Godfrey and a team from the National Optical Astronomy Observatories in Tucson, Arizona, were able to piece together a startling image of a storm system, unlike anything ever seen anywhere in the solar system. First published in 1988, 7 years after Voyager 2 had left the Saturnian system, the patchwork image revealed a puzzling, hexagon-shaped weather pattern sitting around the planet's northern pole. Each of the 6 sides of this vast storm system is around 14,500 kilometers in length, 29,000 kilometers across, and at least 300 kilometers high. It's so vast, the Earth could fit into it at least 4 times over, and it's not just the scale of it that's breathtaking. Swirling inside it are winds whipping around at speeds of over 320 kilometers per hour, and the whole hexagonal storm is completely rotating every 10 hours and 39 minutes. This is a storm on an unimaginable scale, and 30 years later, it still rages on. But despite multiple hypotheses, the atmospheric dynamics behind its shape remain a mystery. As the seasons changed and spring arrived in the northern hemisphere towards the second half of the mission, we got the chance to look at the hexagon that surrounds Saturn's pole. If you flattened it out, it would be about 2 Earths wide. Saturn itself is about 10 Earths wide. So this is a major feature, and it's basically a jet stream. Every time we posted a picture of the hexagon on our website, the hits went through the roof, because I think people were so amazed that you could have something in an atmosphere that had straight sides to it. Carolyn Porco, Cassini mission. From our vantage point here on Earth, it looks as if our atmosphere stretches on and out forever, and yet, by the most widely held definition, it takes a journey of just 100 kilometers to officially make your way through the atmosphere and into space. Of course, atmospheres don't just stop dead. The Earth's atmosphere gradually recedes with increasing altitude, becoming progressively thinner, until by the time you get 100 kilometers up, you'll have 99.999997% of the atmosphere below you. This essentially arbitrary line between the Earth and space is known as the Kármán line. It's a line that was calculated by the Hungarian-American engineer and physicist Theodor von Kármán to be the altitude at which the air becomes simply too thin to support aeronautical flight, where, as he wrote, aerodynamics stops and astronautics begin. Cross this line, and you have officially gone from being a pilot to an astronaut. And you get to join a club that still only contains 561 members at the time of writing. The number of humans who have made it over the line is still so small, because travelling the short hop into space might be slight in distance, but it is large in terms of the power and technology needed to lift anyone or anything that far from the Earth's surface. Gravity binds us tight to our little rock, and despite over 60 years of space travel, it means almost all of us are still very much rooted to the ground. The reason we find it so tough to leave the Earth is because of the mass of the planet, all 5.9 sextillion tons of it, which creates a gravitational pull so strong it requires an escape velocity of around 11.186 kilometers per second to make it off the Earth and into space. That's a lot of speed to counteract the 9.8 meters per second squared of gravitational force that is continually tugging us down. Gravity keeps our species firmly locked to the surface of the planet, but it also keeps a tight grip on everything else on the surface of the Earth, be it solid, liquid, or gas, including the 5.5 quadrillion tons of nitrogen, oxygen, carbon dioxide, and other trace gases that together make up the Earth's atmosphere. In the very simplest terms, the size of the atmosphere of any planet is intricately linked with the mass of that planet. The bigger the mass of a planet, the greater the attraction of gases to its surface. But that's not the end of the story. The ability of a planet to retain an atmosphere is also dependent on a multitude of other factors, including the composition of the atmosphere, its temperature, proximity to the sun, geological activity, the ability of the planet to protect itself from the ravages of the solar wind, and finally the impact of life itself, which has seen our atmosphere gradually pumped full of oxygen. It's the intricate balance of these factors that dictates the endurance and composition of the gases around a planet, each one a unique atmospheric fingerprint. Fast forward through the history of the solar system, and we see a familiar theme again and again around the inner rocky planets. Each of the 4 planets grabbed onto a thin atmosphere, but then the individual characteristics of each planet set in motion its own individual evolution. Mercury, the smallest of the planets and closest to the Sun, lost its atmosphere long ago, with only the merest wisps remaining today. Next there is Earth, sitting in the Goldilocks glow of the Sun. We have clung on to our 100 kilometers of atmosphere in one form or another for billions of years, allowing life to thrive under its warming embrace. Venus, on the other hand, despite starting with an atmosphere likely very similar to our own, has now choked on the 250-kilometer deep toxic atmosphere that blankets its surface today. Each of the 4 rocky worlds has seen its atmosphere ebb and flow over time. But no matter what twists and turns the story of each planet may have taken, there has always been, and will always be, a limit to the size that any atmosphere can grow around these relatively small lumps of rock. Before we return to Saturn to understand how its atmosphere grew in a very different way to those of the rocky planets, we should take a swift look through the history of the Earth's atmosphere in more detail to establish how it began and evolved. Using a combination of geology, climatology, and paleontology, scientists have been able to piece together an immensely detailed picture of the Earth's atmospheric evolution. Far back in the Earth's history, a very different type of atmosphere to the one we see today surrounded the primordial planet. The newly formed Earth had grabbed onto gases from the billowing vapours of the solar nebula, the cloud of gas and dust that the planet had formed from, consisting almost entirely of hydrogen and simple hydrogen-based molecules such as water, H2O, methane, CH4, and ammonia, NH3. This primary atmosphere would have been entirely created by the capture of the nebula's gases by the gravitational attraction of the planet. Slowly, over time, the composition of the atmosphere changed from a hydrogen-based one to one rich in nitrogen and carbon dioxide. We think this shift to the secondary atmosphere was at first triggered by the giant impact of the planetesimal Theia on the early Earth, and then driven by a combination of gases produced during the late heavy bombardment, while asteroids rained down on our planet for millions of years, and the geological activity within the Earth sent vast quantities of gas upwards through all-encompassing periods of volcanism. By the time first life appeared on the planet, the nitrogen-rich atmosphere was stable. But gradually, as life took hold, a new component would begin to appear in the Earth's atmosphere. 2.5 billion years ago, photosynthetic life had become so prevalent, it triggered a tipping point known as the Great Oxygenation Event, during which oxygen was produced by living things at such a rapid rate, it far exceeded the amount of oxygen that was captured from the atmosphere in Earth's geological chemical reactions. The result of this shift to the third atmosphere has been the presence of free oxygen in our atmosphere ever since, providing the energetics to support the rapid evolution of life on Earth. And of course, one of these life forms has become so dominant we've developed a way of life that is now fundamentally changing the atmosphere of our planet for a 4th time, but not for good. Now, with this history of our planet's atmospheric evolution in mind, let's return to the earliest days of the solar system and explore the very different path taken by Saturn. Around 4.5 billion years ago, the young Saturn had grown to become one of the largest rocky bodies in the history of the solar system. At least 10 times the mass of the Earth, it found itself far beyond the warmth of the Sun, locked in its icy orbit, a frozen, rocky world on a scale unlike anything we've ever seen. But time would not stand still for this world. Having grown as large as it could from rock and ice alone, its barren surface would not stay lit by the dim light of the Sun for long. As it continued to grow, Saturn would become a radically different kind of planet, defined not by its rocky surface, but by an atmosphere that would bury it beneath vast volumes of gas, an atmosphere that would not just enwrap the planet, but engulf it. Just like the Earth in its earliest days, as Saturn continued to grow, it drew not just solid material but also gas towards it, from the vast clouds swirling around the embryonic solar system. Huge amounts of the hydrogen and helium left over from the formation of the Sun clung to the vast planet, creating a first atmosphere that may well have been very similar to the earliest one on Earth. But Saturn's early atmosphere would follow a very different course, as it was driven by 2 key differences between the young worlds. First, Saturn had grown far, far bigger than Earth, so by gravitational attraction alone, the volume of gas it could attract towards itself was far greater than anything the diminutive Earth was able to. But it wasn't just size that drove Saturn's atmosphere to grow so rapidly. Located this far from the Sun, the freezing temperatures meant that even the most volatile of gases, could cling on to the planet without being driven off by the heat of the sun. Hydrogen, helium, ammonia, methane, and many other gases that were too light for the smaller worlds of the inner solar system to hold on to were able to accumulate out here, with Saturn's vast mass and the freezing temperatures being enough to draw them in. Trillions upon trillions of tons of gas began to envelop the planet, reaching depths first of hundreds of kilometers and then thousands. And as this new atmosphere grew, it transformed the surfaces below. On Earth, under our canopy of air, it's easy to forget that all of those molecules sitting above your head right now have a weight. If you draw a 1 centimeter square on a piece of paper at sea level, and imagine a column of air stretching all the way up from the square to the top of the atmosphere, it will have a mass of, on average, just over 1 kilogram, exerting a downwards force of 10 newtons onto the paper, a pressure that we call 100 kilopascals, or 1 bar. That might not sound like much, but all of that weight reveals itself in the subtle and not so subtle effects of atmospheric pressure that we can see all around us. For example, the simplest of classroom experiments can reveal the power of the atmosphere by the process of just removing the air from a plastic bottle. The bottle collapses, not because of the vacuum that it creates, but because the bottle cannot withstand the pressure of the atmosphere that is pushing down on it. While 100 kilometers of atmospheric pressure can quickly crush a bottle here on Earth, a much bigger atmosphere can exert pressures that not only are able to shape things on the surface, but also have the power to transform an entire planet. And that's exactly what we think happened to Saturn 4.5 billion years ago. As its atmosphere deepened, the thousands upon thousands of kilometers of gas weighing down on its surface began to generate incredible pressure, heating the rock and ice so much they began to glow. It's thought perhaps that for a brief moment in time, the heat generated on the surface of Saturn by these extraordinary pressures meant that the glow of the planet even outshone the sun. But this was just the beginning. As Saturn matured, the pressure at its core grew to 10 million times the level we experience on Earth. At that level of pressure, matter behaves in extremely strange ways, and the very idea of a planetary surface becomes meaningless. As Saturn took on its new form, the enormous pressures generated crushed and melted its solid core, destroying the rocky world it had been and replacing it with a new world, utterly alien in its characteristics. Saturn had transformed from a world of rock and ice into a wholly different class of planet, a gas giant, a ball of gas so big it could contain 800 Earth-sized worlds inside it, making it the second largest planet in the solar system after Jupiter. At 7:55 and 46 seconds AM Eastern Daylight Time on the 15th of September 2017, NASA's Deep Space Network Antenna Complex in Canberra, Australia, received notification that contact had been lost with one of our greatest space explorers. After 13 years of extraordinary encounters, the Cassini spacecraft had made its last fateful maneuver, plunging headfirst into the atmosphere of Saturn. 45 seconds later, the craft would be gone, crushed by the atmosphere of the planet it had spent over a decade so carefully exploring. Its last image, a monochrome view of the planet's night side lit by the reflected light of the rings, was a picture of its own grave, revealing the location towards which the spacecraft would plummet in its final act of self-destruction as it entered the planet's atmosphere just a few hours later. This was the end of a 20-year mission that had exceeded all expectations. The fourth spacecraft to enter the Saturnian system, following after Pioneer and the Voyagers, Cassini was the first to live there, ultimately spending 13 years and 76 days in orbit around Saturn. During this time, it explored the planet, its rings and its moons, and relayed images and information in a level of detail that would change our understanding not just of the Saturnian system, but of the whole solar system and our place within it. It all began on the 15th of October 1997 at Cape Canaveral, with the launch of the spacecraft aboard a mighty Titan IV rocket. To get to this moment had taken the best part of 15 years, the combined efforts of 28 countries, and a budget of $3.26 billion. But even then, it would be another 7 years before Cassini could truly begin its mission objectives. Getting this 5.5-ton machine across 1.6 billion kilometers of space would require a complex trajectory that would take it on 2 flybys of Venus and out to the asteroid belt, before returning to the Earth 2 years after takeoff for a final slingshot from its home planet that would send the craft hurtling at speeds of 98,346 miles per hour, outwards past Jupiter and on towards its final destination. This complex and high-risk trajectory was designed to exploit the orbital momentum of Venus, Earth, and Jupiter to enable the spacecraft to accelerate, which helped keep the amount of fuel and hence the launch weight to a minimum, while making sure the craft could pick up enough speed to complete its epic journey. However, the trade-off of using this VVEJGA, Venus-Venus-Earth-Jupiter gravity assist trajectory, was a nervous 6-year, 261-day wait for the team back on Earth, as the craft made its convoluted voyage across space. Primary voyage complete, Cassini now faced the life-or-death challenge of slowing itself down with enough precision to enter orbit around Saturn. The tiniest miscalculation would have seen billions of dollars flung into the outer reaches of the solar system and decades of work lost forever. On the 30th of June 2004, the spacecraft began its complex Saturn orbital insertion, SOI, maneuver by flying through the gap between the F and G rings. This maneuver alone was not without serious risk from the potentially devastating impact of particles in the rings colliding with the craft, so Cassini had to carefully orient itself to protect its instrumentation. Once through the ring plane, the spacecraft had to rotate itself once again to point its engine directly along its flight path, so that when the engine fired, it would decelerate the craft by a precise velocity, 622 meters per second, allowing it to fall into the gravitational hand of Saturn. Decelerate too much, and the craft would fall into Saturn. Too little, and it would fly off into outer space. At 8:54 p.m. PDT, Cassini was finally captured by the gravity of this gas giant, becoming the first spacecraft to ever orbit Saturn. A new age of exploration had begun. And over the next 13 years, Cassini would provide an extraordinary return on investment. The Voyagers and Pioneer had given us our first rough glimpses of Saturn's moons, but during its 13 years in orbit round the planet, Cassini did so much more. Not only did it discover a whole host of new moons, it also helped solve countless mysteries around moons we already knew existed, such as Titan and Enceladus, and revealed just how varied the characteristics of the 60-plus moons of Saturn really are. Cassini also allowed us to study, for the very first time, the interactions between Saturn's menagerie of moons and the ring system within which they sit, as well as the structure and history of the ring system itself. One of Cassini's key mission objectives was to explore the characteristics and activity of the vast atmosphere that makes up most of Saturn. Voyager 2 had revealed the presence of a heat source buried deep beneath the planet's cloud tops that seemed to be producing vast amounts more energy, up to 87% more, in fact, than the planet absorbs from sunlight. But what was the source of this heat? And how did Saturn's immense atmosphere organize itself into the vast and intricate weather systems like the huge hexagon? This remained a question that Cassini was charged with solving. Atmospheres can be some of the most spectacular and complex environments found on any planet. From the crushing intensity of Venus's choking atmosphere with its raging winds and sulfuric acid rain, to the thin blue line of Earth, where even on our somewhat milder planet we see endless storm systems. In the inner solar system, the atmospheres of the rocky planets and the weather systems they contain are all powered by a single source, the relentless heat of the sun. All the weather we see on the rocky planets, whether it's a dust storm on Mars or a hurricane on Earth, are driven by the same simple process. It begins with the sun beating down onto the planet's surface, heating the ground, which in turn radiates back, heating up the air closest to the ground. That air expands, which means it becomes less dense, and so the hot air closest to the ground rises. The result of all this rising air is that you get thermals, energetic movement of air from the ground into the upper atmosphere. Over the oceans, exactly the same process occurs, with the heat of the sun evaporating vast amounts of water and lifting it up into the atmosphere. So, in the very simplest terms, all of the extraordinary weather we see on Earth, or any of the other terrestrial planets, is driven by the sun heating the land and sea and causing the air to move around. Travel further out into the solar system, however, and the character of any atmosphere radically changes. The storms on Saturn are among the most violent found anywhere in the solar system. Generated by rich, complex and powerful weather systems, we've been witnessing these giant storms from afar for almost 150 years. Asaph Hall, the great American astronomer and discoverer of the two moons of Mars, was the first to observe one of these storm systems back in 1876. Looking through the largest refracting telescope of the time, the United States Naval Observatory's 66-centimeter telescope located in Washington, D.C., he was able to make out a great white spot sitting in the northern hemisphere of the planet. At the time, Hall wouldn't have known much at all about the phenomenon he was looking at. It was intriguing simply because it enabled him to make the first estimate of the rotational period of the planet. Over the following decades, however, this great white spot was observed again and again, roughly falling into an appearance every 20 to 30 years before slowly fading away. Fortunately for us, the long gaps between each appearance were cut short in December 2010, when a great white spot appeared just 4 years after the previous one. This time, with the Cassini probe in orbit, we had the opportunity to track the evolution of one of these storms close up, from its birth in early December 2010 to its disappearance 8 months later. This vast storm system, resembling in many of its characteristics a simple thunderstorm here on Earth, emerged as a single white spot 1,300 kilometers from top to bottom and 2,500 kilometers from side to side. Over the ensuing months, Cassini was able to follow the storm as it stretched out around the planet. Just a few weeks after its formation, the tail of the storm had extended across 100,000 kilometers, and within 6 months, this great storm had stretched so far, it encircled the whole planet. Cassini was able to image directly for the first time lightning occurring in the middle of this giant storm in broad daylight. The fact that the lightning could be detected on the day side of the planet surprised the Cassini team and suggested that the lightning must be particularly intense to make it visible in such bright light. The lightning flashes are comparable to the strongest lightning flashes that we see on Earth. That was a joy, just to finally witness lightning on Saturn. And we could tell that it was coming from the cloud layer, the deepest cloud layer, which is about 60 miles down, and is the water cloud, the water ice cloud. And that makes sense because lightning is produced on Earth because of updrafts and particles being elevated through an atmosphere, rising through an atmosphere because they're convecting. We had a whole variety of scientific goals at Saturn, and one of the main ones was to understand the meteorology of the Saturn atmosphere and what energizes the winds that we see on it, and so on. And we have affirmed now the belief that the atmospheric systems on Saturn are actually powered by energy from below, from an internal source on Saturn. They're not powered by sunlight, like we have on Earth. Caroline Porco, Cassini mission. Cassini was also able to turn its cameras onto the giant hexagon structure that Voyager 2 had first photographed over 30 years before. This time, with its high-definition, narrow-angle cameras trained on the enormous feature around the North Pole of the planet, Cassini was able to capture the giant hurricane-like storm in extraordinary detail. This vast vortex was measured as 2,000 kilometers across at just the eye of the storm, and with cloud speeds traveling at over 150 meters per second, It's rotating far faster than any hurricane we've ever seen on Earth. Exactly what causes this, or any of the giant storm systems we've witnessed on Saturn, is still not fully understood. But one thing we absolutely do know is that this far out from the Sun, these weather systems cannot be driven primarily by the Sun's heat. With Saturn receiving 100 times less of the Sun's energy than Earth, something else must be driving its weather, something that creates the same great upswellings of heat we see on Earth, but that on Saturn is entirely generated from the interior of the planet. As yet, we've not been able to peer deep enough into Saturn's interior to see directly what happens inside this strange world. But in the last couple of years, we've come closer than ever. As we've accumulated evidence from Pioneer, Voyager, and of course Cassini, and combined it with our increasingly sensitive ground-based observation, we've been able to start piecing together a detailed journey into the heart of the planet. By just touching the cloud tops of Saturn, alive with great storm systems and flickering with immense bolts of lightning, they have given us the first hints of the truly strange world that must lie beneath, and the mysterious energy source that brings this planet to life. Our journey deep into the interior of Saturn begins not with clouds, but with rain. At the very outer edges of its atmosphere, in the space between the closest ring, the D-ring, and the planet itself, we've discovered the phenomenon of ring rain, an endless downpouring of material falling from the rings into the upper atmosphere of the planet below. We know this because as Cassini took its final fatal plunge on the 15th of September 2017, it flew through this uncharted no-man's land and was able to make the first direct measurements of the rain falling from the rings. Using the ion and neutron mass spectrometer, it measured the rate at which the rain was falling from the rings, a staggering 10,000 kilograms of material every second. It was also able to reveal that the ring rain is comprised of a mix of hydrogen, water ice, and a surprising quantity of complex organic compounds like butane and propane, all showering down onto the planet and changing the chemistry of its upper atmosphere in ways we are only just beginning to understand. Cassini then began its final historic dive into the upper atmosphere of Saturn, struggling to keep its antennae pointing towards the Earth as it was buffeted by the increasing turbulence, while continuing to send a stream of precious data back to us, right until the very end. Travelling at around 123,000 kilometers per hour, Cassini entered Saturn's upper atmosphere at 3:30:50 PDT, 1,900 kilometers above the planet's cloud tops. This was the first time scientists had ever been able to sample the atmosphere directly, our distant human envoy touching the gas giant for the very first time. Over the next few seconds, Cassini increased the use of its altitude control thrusters to steady its rapid descent into the thin outer reaches of Saturn's atmosphere and keep the antennae pointing towards Earth for a final few seconds of contact. But this was a losing battle. Over the next minute and a half, the growing density of the upper atmosphere rapidly began to increase the friction on the forward-facing surfaces of the spacecraft, raising the temperature at high speed, and creating an unfolding thermodynamic situation that Cassini had not been designed to withstand. At precisely 3:30 PDT, 1,500 kilometers above the cloud tops, Cassini finally lost its battle for control. After 20 years in space, 13 of which were spent exploring Saturn, and having travelled a distance of 7.9 billion kilometers, this battered explorer was no longer able to maintain a stable flight path through the increasingly dense atmosphere. Beginning to tumble and roll, the last few bytes of data left its antennae streaming the 90-minute journey back to Earth, and the mission was long over before that final contact reached our planet. Precisely what happened next to the little spacecraft as it fell into the grip of this giant planet remains no more than well-informed conjecture. Using computer models to predict its final seconds, the Cassini team were able to watch only in their mind's eye as the craft tumbled chaotically through the atmosphere. Travelling at 144,200 kilometers per hour, just 1,100 kilometers above the cloud tops, and with temperatures rapidly increasing, every component of this unprotected machine began to disintegrate. With all computer systems failing and the spacecraft blind and deaf to its surroundings, it began to break up, its gold insulation blanket rupturing first, before the external carbon fiber structures of the spacecraft itself began to fracture and fragment. Then, with the rings gleaming in the sky above it, and the yellow cloud tops beckoning below, what was left of Cassini streaked across the Saturnian sky, blazing with temperatures higher than the surface of the sun. The gas tanks of propellant that helped steer the craft on its epic voyage blasted apart the remaining structures into 1,000,000 different pieces, which in a final spectacular moment lit up a little corner of the majestic planet with the burning debris of its greatest explorer. Cassini was dead, but its final journey was far from over. Over the following minutes, the debris scattered and fell through the cloud tops, deep into the planet's interior, until finally the atoms of this beloved machine, built by human hands millions of kilometers away on a faraway world, came to rest in the heart of the planet. Cassini and Saturn, inseparable forevermore. Where the debris of Cassini finally ended up, we can only imagine. But the data from this extraordinary mission that was collected right up to its very end has helped us to dive deeper into the detail of Saturn's interior than ever before. As the wreckage scattered and fell from the upper atmosphere, it would have fallen through the very first cloud tops of the planet. Here, with temperatures ranging from -170 to -110 degrees Celsius. The clouds are made not of water ice, but frozen ammonia. It's these ammonia ice crystals that give Saturn its characteristic pale yellow color, a color that we can see shining back at us with even the most modest of earthbound telescopes. Beyond this upper layer of cloud, as the pressures begin to increase and the temperature rises, huge clouds of water ice form a thick layer, the water molecules perhaps long-lost remnants of the building blocks of the icy world that Saturn once was. It's here, amongst the vast cloud systems, that lightning more powerful than anything we see on Earth illuminates the sky, within storm systems that rage for months on end. Cassini gave us the first still and moving images of these lightning storms, and enabled us to predict the next great transformation that will happen within the planet's interior. Every couple of decades, Saturn surprises us and breaks into a fit, and actually erupts with really major storms. These are global storms, and they last for about 6 months to a year. The one that we saw with Cassini in 2010 was so powerful that our calculations show it was the most powerful storm we've ever seen anywhere in the solar system, even Jupiter, in terms of its central conductive storm system. We had an amazing chance to see that during the Cassini mission. And then when we looked at those clouds that it was forming, we found amazing things in the storm clouds of Saturn. We found that it had water ice. And this really blew our minds because water should be sequestered deep down in the atmosphere. You should not find it at the top of the atmosphere. It only gets there when you have huge convective updrafts, and we're talking updrafts that bring gas up from 100 miles down. And on the Earth, we only see gas going up and convection going up only about 10 miles. Here you have storms 10 times bigger, very powerful storms, lifting things up from 100 miles down and bringing up the water from below, which was probably actually a mixture of gas and water. But then it brought it up and it turned into ice, and the component of water ice in it really shocked us. Kevin Baines, Cassini mission. We now think that around 100 kilometers below the visible atmosphere, the same distance from the surface of Earth to space, with temperatures inside Saturn's lightning reaching almost 30,000 degrees Celsius, this lightning transforms methane gas in the atmosphere into huge clouds of carbon soot, carried higher into the atmosphere on great convection currents. We think that it's these specks of carbon-producing lightning that can explain the mysterious dark clouds that Cassini was able to observe and image over many years. This particulate matter rains down from the upper cloud layers until, at a depth of 1,500 kilometers, we think the enormous pressures begin compressing this soot into graphite, which then falls further into the depths of the planet. We then think that at around 6,000 kilometers down, this graphite undergoes a truly extraordinary transformation. With pressure and temperatures rapidly increasing, the graphite is compressed into solid diamond that rains down for at least 250,000 kilometers. Estimates suggest at any one time 10 million tons of diamond hail is raining down within the planet, from specks of diamond dust just a millimeter across to chunks as big as 10 centimeters. Perhaps even for a brief moment in time, some of the charred, carbonized remains of the Cassini probe made it down into these depths and transformed into diamonds as well, falling further into the planet it had helped us understand. But eventually, even these diamonds will ultimately succumb to the enormous pressures of Saturn's interior. Around 30,000 kilometers into the atmosphere, where temperatures reach 8,000 degrees Celsius, the diamond melts and forms liquid diamond raindrops that continue to descend into the abyss. It's here, around 40,000 kilometers down into Saturn's interior, that we believe the source of Saturn's energy, the energy that drives all the storms and weather we see playing out on its surface, is finally revealed. Here, the pressures are so intense that the hydrogen that makes up over 96% of Saturn's mass is compressed into a vast ocean of liquid hydrogen that is saturated with helium gas. Under these enormous temperatures and pressures, the helium precipitates out and falls like rain through the ocean, depleting the levels of helium in Saturn's outer layers, which explains the lower than expected amount of helium first measured by Voyager 1 in 1980. It's a process that, through the simple action of friction as the molten helium rain falls, creates an incredible amount of heat, and we think this is the engine, the energy source that helps power Saturn's ferocious weather and drives its entire atmosphere for tens of thousands of miles in every direction. Finally, we reach the interior of Saturn, a layer where the liquid hydrogen is so compressed it starts to behave like a liquid metal, and the helium itself may accumulate into a metallic shell surrounding the core. Beyond here, we do not know if a rocky core remains as a remnant of Saturn's long-lost past, or whether under these enormous pressures the possibility of solid rock is no longer viable. Whatever lies at the center of Saturn, we estimate that this core region has a mass of around 20 times that of the Earth, and a diameter of around 25,000 kilometers. And here, perhaps, a few tiny fragments of Cassini might have come to rest in the ancient heart of the planet. Saturn has lived a life of incredible drama. The evolution from rocky beginning to the extraordinary gas giant we see today took just a few 100 million years of rapid transformation. And yet, throughout almost all of this time, one thing has been missing. We now think Saturn was born naked and has lived out the vast majority of its existence without the structure that makes it more iconic than anything else. Saturn is a world defined by its rings. Ask a child to draw a planet, and more often than not they'll draw something that looks remarkably like Saturn. The particles in the rings of Saturn are almost impossibly delicate and intricate. Most of them are no bigger than snowflakes, but some are as large as houses, orbiting the planet at 1,800 kilometers per hour, in one of the most beautiful structures we have ever laid eyes on. One of the reasons why the rings have captivated us for so long is that, despite their vast distance from the Earth, if you look through a simple telescope, they shine back at us, bright against the night sky, reflecting the sun's light as powerfully as the planet itself. For years, the age and origin of the rings has been argued over, with conflicting evidence supporting two very different hypotheses. On one side, the argument has been made that a ring system as dense as Saturn's must be an ancient structure shaped from the remnants of the planet's formation. On the other side of the fence, the evidence has been used to suggest that the rings must be youthful, a relatively recent addition to the ancient planet. The brightness of the rings is not only beautiful but also rather surprising. The solar system is not a very clean place. In fact, it's full of dust and dirt, and so we would expect any ice crystals that hang around for any length of time to inevitably get dirty. We also know that if ice gets dirty, it doesn't reflect sunlight anywhere near as brightly. So in the case of the rings, we would have expected, if they had been present over the lifetime of the planet, all of those particles and blocks of ice would have become increasingly less reflective. If they had formed anywhere near the birth of Saturn, they would almost certainly be invisible to us now, or at least incredibly faint. And yet they shine brightly, as if they were made just days ago. Variations of this debate have been rumbling since the 18th century, but that all changed with Cassini. During its 13-year tenure around the planet, the probe was able not only to see Saturn's rings like never before, but also provide us with direct evidence about their density and composition. And this information is helping scientists to solve the puzzle of the rings once and for all. For the very first time, Cassini was able to take physical samples directly from the rings and surrounding dust, using the Cosmic Dust Analyzer, CDA, mounted on its exterior. This highly sophisticated piece of technology is basically a multi-million-dollar bucket, but a bucket that can detect particles 1/1,000,000th of a millimeter wide, that's smaller than a virus, and determine the particle's size, speed, and direction of travel, as well as their chemical composition. By measuring the dirt and dust from the Saturnian system falling onto the rings, Cassini has allowed scientists to rewind the clock on the rings and provide direct and compelling evidence that the ice particles are nowhere near as dusty as they would be if they were an ancient part of the planetary system. This confirms the long-held belief that the rings are so bright because they are young. And in fact, the evidence gained from Cassini's CDA suggests they are far younger than we ever imagined. Latest estimates suggest they're somewhere between 10 to 100 million years old. That's nearly 4.5 billion years younger than Saturn itself. So where did they come from? Once again, Cassini provided a tantalizing clue. In its final few days, Cassini embarked on a series of almost reckless orbital trajectories that were so risky to the spacecraft's safety they would never have dared to be attempted earlier in its mission. Taking the probe closer to the planet than ever before, the team flew Cassini repeatedly through the gaps between the upper atmosphere of the planet and the inner rings. Throughout September 2017, as it performed 22 of these perilous dives, Cassini was able to take measurements of the gravitational tug of both the planet and the rings. This data was then used to calculate the mass and density of the most substantial ring in the Saturnian system. The B ring makes up 80% of the mass of all the rings, and yet Cassini's measurements suggested that the total mass of the ring was surprisingly low. This result, although not conclusive, strongly points to the fact that the ring's origins lie not in the ancient past during the formation of the planet itself, but to a far more recent and dramatic event involving one of the worlds trapped in orbit around it. The rings, it seems, were born of a moon. Saturn has 62 large moons, and countless smaller ones, that range in size from planetary-scale objects like Titan to smaller, irregular lumps of rock like Aegeon. And we're still hunting for new moons to add to the list. On its travels, Cassini spotted 2 objects within the F ring that are potential candidates for moonhood, but as yet S/2004S6 and S/2004S3 remain unverified and unconfirmed. Within this menagerie of worlds are an endless variety of clues written into the size, form, and surface features of the moons that allow us to read the history of the Saturnian system, revealing the often violent and volatile events in its past. Mimas is otherwise known as the Death Star moon, and was first spotted in 1789 by William Herschel, who is immortalized in Mimas's eponymous huge impact crater. Mimas is just 396 kilometers across, and the Herschel crater covers 130 kilometers of that surface. A deep scar that tells us that once, long ago, there was a giant impact that almost destroyed the Moon. Iapetus, the third largest of Saturn's moons at 1,500 kilometers across, is almost planetary-sized and has a distinctive two-tone coloration, half light and half dark. Iapetus was discovered by Giovanni Cassini himself in 1671 and has another distinctive feature that we have long puzzled over. Running around 3/4 of the Moon's diameter is a massive equatorial ridge. It's one of the highest mountain ranges in the solar system, 20 kilometers from the peaks to the ground below, and it's thought this may have formed because a ring that once circled the Moon collapsed onto its surface. Hyperion is the strange sponge-like moon that tumbles around in Saturn's orbit, which in 1848 was the first non-spherical moon ever to be discovered. To this day, it remains a mystery as to what caused its punctured surface and irregular shape, and it's been suggested that Hyperion is in fact a remnant of another moon that broke up long ago. Pan, the small walnut-shaped moon that was discovered less than 30 years ago from the analysis of images taken by the Voyager 2 probe, is named after the Greek god of shepherds. It's so named because Pan is a shepherd moon, clearing the orbit of the Encke Gap, a 325-kilometer space within the A-ring. Its distinctive equatorial ridge is thought to be made of material that's been swept up and accumulated as it clears its path through the ring. Cassini's endless stream of images and data until 2017 has enabled scientists to analyze each of the moons in ever more detail, and it's become increasingly apparent that they are intimately linked with the ring system they orbit. Many of the moons are made of exactly the same material as the rings themselves. Mimas, Iapetus and Hyperion are ice moons, composed almost entirely of frozen water ice, with only the smallest amounts of rock in their makeup. From the evidence that we've been able to read on their surfaces, it seems almost certain that through 4 billion years of violent interactions, at least some of the moons of Saturn must have both come and gone over the planet's history. All of this begins to point us towards the idea that perhaps the most intriguing moon in Saturn's long history is one that is now entirely missing. Around 200 million years ago, as dinosaurs roamed the Earth, we now believe a long-lost moon orbited close to the planet Saturn, a moon perhaps 400 kilometers across and formed almost entirely of ice. This was a doomed world, orbiting too close to resist the immense pull of Saturn's gravity, its fate sealed at the moment of its birth. It was the French astronomer and mathematician Edouard Roche who first suggested the existence of this long-lost moon in 1848. He christened it Veritas, after the Roman goddess of truth, who according to legend is supposed to have hidden in the bottom of a holy well. Roche had postulated the existence of this moon while exploring a particular dynamic of celestial mechanics that describes the potentially violent gravitational relationship between two celestial bodies. He was able to demonstrate that when a moon moves within a certain distance of the planet it is orbiting, it can cross a threshold where the force of gravity is so strong, the moon will be ripped apart. This distance has become known as the Roche limit, and is dependent on many factors, including the mass, radius, and physical characteristics of the moon and planet. Outside of the Roche limit, a moon can exist in happy equilibrium with its planet, orbiting in the gravitational grip of the larger body while maintaining its physical integrity. But if that same moon's orbit degrades to the point where the Roche limit is crossed, the tidal forces exerted on the moon exceed the gravitational attraction that holds the moon together in a sphere, resulting in the moon's destruction. This relationship applies to any moon-planet system, including our own. Here on Earth, we see the relationship between our planet and moon on a twice-daily basis as the tides ebb and flow across the planet. These tides are caused by the difference in the gravitational pull of the moon from one side of the Earth to the other, and that difference, although subtle, is powerful enough to move entire oceans with the forces of tidal gravity. Just as the moon creates tides on Earth, so the Earth also has a tidal effect on the moon. And because the Earth is much greater in mass, that effect is more powerful than you might think. The Earth's pull is in fact powerful enough to deform the moon's surface. Even today it causes moon tides on the lunar surface, where it causes the rock to rise and fall. But the effect was even stronger 4 billion years ago, when the moon was nearly 17 times closer to the Earth. Back then, the pull from our planet caused a tide of solid rock to rise and fall by many meters, and if the moon had ever come any nearer, it would have crossed the Roche limit and been ripped apart. When Edouard Roche first formulated the equations calculating this line, he realized that the result of such destruction would not just be the obliteration of a moon, but also the creation of millions upon millions of fragments, the debris of the moon orbiting around its destroyer. He also deduced that in time these fragments would form once again into the most delicate of structures, a system of rings, under the influence of the planet's gravity. In one of the more gruesome tales from classical mythology, Saturn, the Roman god of time and harvest, actually ate 5 of his newborn babies to prevent them taking his power. Now, Cassini has shown us that, at least metaphorically speaking, they weren't far wrong. We now think that 10 to 100 million years ago, just beyond the outer reaches of Saturn's vast atmosphere, an icy moon orbited, gradually edging closer and closer to that tipping point, the Roche limit. As Saturn's immense gravitational force pulled at it, this great moon began to rupture, and in a moment undoubtedly worthy of even the greatest of mythological stories, up to 30 million trillion tons of ice, more than 30,000 times the weight of Mount Everest, broke apart in orbit and spread out around Saturn. Traveling at tremendous speed around the planet, it's likely that this debris quickly scattered to encircle the giant planet, and in the space of no more than a few days, Saturn's iconic rings had been born. Today, this giant ring system has evolved into the intricate structures we can see in the night sky. Saturn's powerful gravity has helped keep its near-perfect elliptical shape, but an endless series of collisions have caused it to gradually flatten out. Now this debris forms a disk wider than Jupiter, yet on average just 10 meters thick. With moon-sized chunks of ice orbiting through this structure, great voids have been cleared, turning one ring into many. In places, moons have pulled particles of ice upwards to create strange peaks over a kilometer high, which cast spectacular shadows across the rings. Saturn, once a tiny world of rock and ice, a world that has undergone repeated transformations, has today become the solar system's greatest jewel. And Cassini, our most intrepid of explorers, has forever deepened our understanding of the life story of this planet. Yet perhaps Cassini's greatest gift is not in its revelations of the past, but in the glimpse it has given us of the future. Because just beyond Saturn's rings, Cassini would discover a hidden treasure, a world that may hold answers to some of our deepest questions about our place not just in the solar system, but in the universe. One of the unmistakable jewels of the Saturnian system is Titan. A giant, it is the second largest moon in the solar system, and this planet-sized satellite is larger than the smallest planet Mercury, and 50% bigger than our own solitary moon. Discovered by Dutch astronomer Christian Huygens in 1655, it has held its secrets close for centuries, cloaked by thick clouds. The only moon in the solar system with a dense, distinct atmosphere of its own, from afar Titan hinted at being far more like a planet than a moon. It would take a mission of breathtaking ambition to finally peer under her veil and see the wonders that lay beneath. On Christmas Day 2004, after a 7-year journey across the solar system, the Cassini probe released its sibling craft Huygens, setting it off on a 4 million kilometer path to Titan. Simple in appearance, Huygens looked as if it had borrowed its design from the classic cartoon UFOs of the 1950s. But nothing was simple about Huygens. This was a highly advanced spacecraft about to begin one of the most complex maneuvers ever attempted in the history of human space exploration. As it made its 3-week journey towards Titan, the team of ESA, European Space Agency, scientists who had dedicated a lifetime's work to the project, watched on, hopeful but helpless. From the moment of release, they had lost direct control of the probe and were unable to send it commands. Instead, as planned in the mission protocol, Huygens was now entirely controlled by the onboard autonomous computer systems. All they could do was watch and wait to see if Huygens could fulfill their ambitions by becoming the first probe to land in the outer solar system, on a moon other than our own, in the most distant landing of any spacecraft. To succeed, Huygens would have to execute a perfectly controlled landing protocol designed to use Titan's atmosphere as an aerobrake, before employing a parachute system to deliver the scientific instrumentation to the surface. And all after awakening itself from a 6.7-year intergalactic sleep. The probe had remained in an entirely dormant mode, except for a 6-monthly self-health check, and only at the point of separation from Cassini was the timer set to wake the probe up, 15 minutes before entering the atmosphere of Titan. The proposed landing site for Huygens also held much uncertainty, chosen to be in the southern hemisphere of Titan, 192.3 degrees west, 10.3 degrees south to be precise. The area was surveyed by Cassini's cameras from an altitude of 12,000 kilometers, and appeared to be near a site that had many of the characteristics of a shoreline. Landing into an extraterrestrial ocean had been part of Huygens' original design, so in theory the craft was expected to survive any splashdown into a liquid surface on Titan. On the 14th of January 2005, the 318-kilogram probe entered Titan's atmosphere, 1,270 kilometers above the surface, and began its descent protocol. On-board accelerometers monitored the craft's deceleration, waiting for the precise moment to trigger the explosive bolts that would blow off the front heat shield and back cover, and release the pilot parachute, which would then pull out the main parachute, slowing the 2.7-meter wide craft from its nearly 2,000 km/h descent, and allowing it to drift safely to the surface. All of this would need to play out perfectly, while more than 1 billion kilometers away, a group of nervous humans sat in near silence in mission control, waiting for the first telemetry to confirm that Huygens was safely on the ground. Every second was utterly critical, because Huygens had no more than 3 hours of battery life, and with an expected 150-minute descent, that meant not much more than half an hour's activity on the ground. For a mission that had cost millions of dollars and taken decades to plan and execute, its success would depend on this incredibly short window of exploration. Despite its sophistication, Huygens could not communicate directly in any detail with Earth. Instead, all of its detailed telemetry would need to be relayed back to Earth via Cassini's communications system. This meant very little was known about the probe's status during the 2-hour and 27-minute descent. But at precisely 11:38 UTC, the Robert C. Byrd Greenbank Telescope in West Virginia picked up the weakest of carrier signals generated by Huygens' 10-watt internal transmitter to confirm that Huygens had arrived safely on the surface. This extraordinary probe was now alive and active on an alien moon orbiting Saturn. Just under 5 hours later, the Cassini probe orbiting far above the moon's surface began relaying the precious data from Huygens back to Earth. And by 1945 that evening, the first extraordinary picture was released, showing a view from Huygens about 16 kilometers above the fast-approaching surface. This was space exploration on an awesome scale. A photograph taken by a tiny space probe floating down on a parachute to the surface of a moon, orbiting a planet over 1 billion kilometers from Earth. It's instantly apparent that this is no featureless rock. The channels running across this picture are recognizable as the geology of a world shaped by liquid. covered in drainage channels crossing the landscape into what looks like a lake bed or sea, and more was to rapidly follow. Just a few minutes later, the first image from the surface arrived on Earth. The first view of the surface of a world in the frozen far reaches of the solar system. It's an image that is worthy of the very closest of inspection, because, as always in science, the more you know about it, the more wonderful it gets. What we can see in this extraordinary image is something that is exactly like a floodplain or riverbed here on Earth. We can say this with some certainty because you can see that the rocks are abraded. They've been smoothed by the action of a liquid flowing over them. But there are no rocks. Huygens was able to confirm that these are in fact boulders of frozen water ice, sculpted on the freezing temperatures of Titan's surface. These rocks of ice are sitting on a surface that, as one Huygens scientist described it, is like snow that has been frozen on top. If you walk carefully, you can walk as on a solid surface, but if you step on the snow a little too hard, you break in very deeply. So if the temperature is so cold on Titan that rocks are made from water, what liquid is flowing over the rocks of ice, carving the riverbeds and floodplains? We'd known for some time from spectroscopy carried out here on Earth that Titan had an atmosphere rich in methane gas. And many scientists had wondered if this could mean that liquid methane existed on the surface. But it was only when Huygens was actually on the surface and its instruments began testing the atmosphere directly that we could begin to see just how alien this world was. For an unexpectedly long 70-minute period, Huygens was active on the surface, detecting significant amounts of methane in the air. Huygens was also able to confirm that the surface temperature on Titan was a freezing -180 degrees Celsius, combined with an atmospheric pressure equivalent to 1.4 atmospheres here on Earth. The measurements confirmed that on Titan, methane was not a flammable gas, but potentially in abundance on the surface, in liquid form. Titan, it seemed, was a wet world, not with flowing water, but with liquid methane driving ice-like rocks down mountain channels and out into open floodplains. But despite early speculation, Huygens had not made a splash landing. It lay in a dry riverbed, and after surviving for just a few hours, its battery ran dead. This miraculous explorer switched off without directly detecting liquid methane on the surface. It would be 2 years later, as Huygens lay frozen and dead on the surface of the Moon, that the very much alive Cassini probe would fly high above the south pole of Titan and beam back an image that would provide a unique view seen nowhere else in the solar system beyond Earth. This was our first glimpse of liquid on the surface of an alien world. A lake composed of methane, ethane and propane near the south pole of Titan. Named after one of the Great Lakes of North America, Ontario Lacus is like nothing we have ever seen on Earth. A 15,000 square kilometre lake of hydrocarbons, whipped by winds that are clearly eroding the shoreline. And Ontario Lacus was just the first. Today, thanks to Cassini's years of observation and photography, we have discovered more than 40 lakes of liquid methane, including Ligeia Mare, a vast body of liquid hydrocarbons with a shoreline over 200 kilometres in length. We've seen mysterious bubbles rising from its depths. Kraken Mare is the largest known body of liquid we have so far found on the surface of Titan. This hydrocarbon sea covers an area of 400,000 square kilometres, 5 times larger than Lake Superior, and has a depth that we suspect descends to 160 metres. We've seen waves in this sea, and islands and currents, endlessly being filled by the flash floods of methane rain that we are certain fall on the highlands surrounding the sea, feeding the rivers and streams that flow into it. Earth, it seems, has a strange cold twin, a moon, not a planet, that is millions of miles away, where lakes are liquid methane and mountains are made from frozen water ice, as hard as rock. What's also fascinating and tantalizing is that Titan has a complex chemistry, a carbon chemistry. the chemistry of life. We have found molecules like hydrogen cyanide, which are the building blocks of amino acids, molecules like vinyl cyanide, which chemists and biologists speculate could form some sort of cell membrane. In fact, all of the ingredients for life are present on the surface of Titan today. That doesn't mean there is life. In reality, very few scientists think there will be life on Titan today, as it is, after all, minus 180 degrees Celsius at the surface. But with a little heat, it might be a very different story. In a few billion years' time, as the light of the dying sun reaches out beyond the inner solar system to touch the outer reaches with its warmth for the very first time, Titan will begin to warm. Its mountains of ice will shrink and melt, and the frozen water they contain will replace the liquid methane, which will have evaporated away into space. Mountains will become oceans, and in a strange twist of fate, at the end of the life of our star, perhaps the solar system's last water world will be born. David Grinspoon believes it's a prediction we cannot rule out. Titan today has all these juicy organics pooled and lying on its surface, and yet it's so cold and so dry that it may be that nothing is really happening biologically there. But we can imagine a time in the far future when the sun has heated up to the point where the inner solar system has become uninhabitable, where Titan may become quite habitable. That methane greenhouse will become more powerful as the sun gets hotter, and at some point that icy crust will start to melt, and you'll have large pools of liquid water on the surface full of all those complex organic chemicals, and that is a recipe for the kind of place where the origin of life can happen. So even if Titan doesn't have life today, and that's something we still have to search for, there's every reason to imagine that at some point in the future, it could be a great place for biology. It's easy to think of habitability as a permanent feature of worlds, a defining characteristic, if you like. Earth is habitable because it's in the Goldilocks zone around the sun, not too close and not too far away. But it's more complicated than that. Solar systems are dynamic places. Over long timescales, planets change orbits and their parent stars evolve, and worlds that were once heaven can become hell. We now understand that Earth has been a fortunate world, an oasis in a constantly changing solar system that's maintained a stable climate, perhaps against the odds. For the 4 billion years it's taken complex living things to evolve. We don't know how many planets like Earth are out there amongst the stars, where the ingredients of solar systems have assembled into structures capable of dreaming of other worlds. But we must consider the possibility that there are very few, and that would make Earth, and us, extremely rare and precious. Nearly 1 billion miles from the warmth of the sun, on the outer edge of Saturn's rings, lies the icy moon of Enceladus. A small moon, about the size of Iceland, Enceladus is the most reflective object in the solar system. Over 90% of the light that hits it bounces back. That's because the surface of this ice-covered moon is covered by crevasses just like we see on the surface of glaciers here on Earth. But on Enceladus, these cracks in the ice occur on a much grander scale, with some stretching for over 100 kilometers. But for all that's going on the surface, it's what we discovered beneath Enceladus's shell of ice that must rank as one of the greatest surprises in 21st century space exploration. A surprise that had been hiding in plain sight for decades. The first photograph of Enceladus was taken by Voyager 1 in 1980. It was actually captured unintentionally, a moon photobombing the planet, and nobody even noticed Enceladus until over 35 years later. But when the image was eventually enhanced, a remarkable feature, no more than a misty blob, began to emerge on one side of the moon. 24 years later, Cassini saw exactly the same thing, but this time in much more detail. As Cassini approached Enceladus, the anomaly revealed itself. Giant plumes of water vapor and ice were erupting from its surface. Over 200 kilograms of material was being released every second, feeding one of Saturn's outer rings and helping to replenish it. These discoveries inspired the Cassini team to take an audacious risk. Piloted from nearly 1 billion miles away, Cassini was guided dangerously close to the plumes, and using its cosmic dust analyzer, was able to actually touch the plumes of ice and collect a sample from one of the eruptions. As Michel Doherty, scientific leader on the Cassini project, explained, the really close flyby that we had of Enceladus, where we were 25 kilometers above the surface, is probably closer than any spacecraft has been to a planetary body before. And the Cassini mission team said they'd never do it again because we were in the atmosphere, well, in the plume, which was really dense. They didn't lose control of the spacecraft, but they felt they might, because the mag boom used to stickle from the side of the spacecraft, and that almost started tumbling the spacecraft. What the scientists discovered, though, thanks to this and a series of similar flybys, was breathtaking. The plumes were spewing out of fissures known as tiger stripes, being projected from deep within this ice world, rising up from an ocean of salty liquid water beneath the ice. How could such an ocean exist in the far frozen reaches of the solar system? The answer lies once again in the power of Saturn to control the destiny of the moons in its dominion. Unlike the long-lost moon of Veritas that was destroyed by the might of Saturn to create its rings, in the case of Enceladus, its mother planet has breathed life, not death, into its structure. Enceladus orbits Saturn, and the planet's vast gravitational force pulls at the moon, holding it in orbit. But every couple of rotations, another larger moon called Dione aligns with Enceladus, drawing it back. This repeated tug of opposing tidal forces stretches and squeezes the moon, warming its core and melting its icy interior. Exactly the same gravitational forces that destroyed one of Saturn's moons are now breathing life into another. But it's what Cassini found in the chemical makeup of the plumes that changed everything, because as it analyzed the columns of water, it discovered complex organic compounds and silica particles, direct evidence that deep below the ice at the bottom of a salty ocean of water, there were hot hydrothermal vents, exactly like the ones from which we believe life emerged on Earth almost 4 billion years ago. Out in the frozen outer reaches of the solar system, Cassini has given us a glimpse of the world beneath the ice on Enceladus, and revealed a warm, watery oasis, a world in which it really is possible that life could exist. Exciting though the prospect of life in space is, if it is out there on Enceladus, it's likely only to be home to the simplest and most primitive organisms, and given how violent and changeable Saturn's past has been, this world may have arisen relatively recently. We don't know how long Enceladus has been active, but if it's only tens or even hundreds of millions of years, that might not have been enough time for life to get going. And despite all the caveats, the very fact that the Saturnian system holds the potential to host life is a truly remarkable discovery, and one that compels us to explore even more. But for Cassini, the brave new world under the ice of Enceladus was a bittersweet discovery. 13 years after it arrived in orbit around Saturn, as Cassini's fuel finally began to run dry, the team at NASA realized it couldn't risk letting this probe crash land on Enceladus and contaminate a potential habitat for life. As Carl Murray explains, because we now knew Enceladus was a potentially habitable environment, we couldn't risk Cassini crashing into it or coming near it because there might be microbes hitchhiking on the spacecraft, and we couldn't allow contamination of Enceladus. So we consciously picked an end of mission that would use up its fuel and then send the spacecraft into the giant planet itself. We journeyed out across space to Saturn to see this great beauty up close, but in the end we were rewarded with insights that hit far closer to home. As is so often the case in exploration and science, the real treasure was found in the unexpected shadows. On this mission, it was in the shadow of the rings, because there we found a tiny world with the potential to harbor life, to provide reassurance that for the first time, we might not be alone. Would such a discovery matter? Yes, it would. At this moment in history, we are, I think, in need of reassurance, or perhaps a reminder, that there is great beauty and knowledge and perhaps even life and meaning beyond our shores. We will, I'm sure, go back to Saturn and its moons, explore deeper, stay longer, and maybe one day even visit there ourselves. We don't yet know what we will discover, but we can be sure it's a story that has only just begun. Cassini's discoveries have profoundly changed our understanding of the Saturn system, from the planet itself to detailed structure in the rings. We now know what the surface of Titan looks like, and we have also pierced through that haze with the radar to map it all out. The lakes and seas are liquid methane on the surface of this moon. And then, of course, the big discovery of geysers coming out of the south pole of Enceladus, flying through those geysers, sampling, tasting, measuring what's coming out, the gases and the particles, and finding not only do you have a lot of water from that liquid water ocean, but you have organics. You have nitrogen, you have methane also. So you have sort of the key ingredients, carbon, hydrogen, oxygen, nitrogen, the building blocks for life. It's so intriguing to find a moon that's only 500 kilometers across with a liquid water ocean, just one of a suite of ocean worlds in our solar system. And perhaps life is just next door.